Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and even the biggest questions are allowed to unfold slowly, without any rush at all. Tonight we're turning our attention towards something bright, familiar, and perhaps a little intimidating if you think about it for too long: the sun. Not the idea of the sun, not the gentle glow it casts across your room in the morning, but the real thing. A massive blazing sphere of plasma, quietly holding the entire solar system together while sitting at a distance that feels both enormous and strangely manageable, depending on how you think about it. Because here's a curious thought to begin with. You feel the sun right now, even if it's nighttime where you are. The warmth stored in the ground, the air, even in your own body, all of it traces back to that same distant star. It's already touching your life in ways that are easy to forget. And yet, if someone asked you a very simple question, how close could you actually get to it? Not in theory, but really, physically, with real materials, real limits, and real consequences, the answer becomes much less obvious. Would you last seconds? Minutes? Could anything survive longer than that? And more importantly, what does close even mean when the thing you're approaching doesn't have a solid surface at all? Before we start easing into those answers, let me ask you something simple. Where are you listening from tonight? And what time is it in your part of the world right now? It's a small question, but it's always a comforting one. A reminder that while we're all sharing this same quiet moment, we're scattered across different places, different evenings, different little pockets of time. Some of you might be winding down after a long day, others might just be settling into bed, and a few might be listening in the middle of the night when everything feels a bit softer and quieter. If you find this kind of gentle exploration relaxing, or even just a pleasant way to slow your thoughts down, feel free to give the video a like, maybe subscribe if you'd like more of these calm journeys. It helps this small, quiet corner reach others who might be looking for the same kind of peaceful curiosity. Now, let's take things slowly and begin. Instead of jumping straight toward the sun, it helps to start somewhere much closer. Right here, on Earth, where the sun feels manageable, warm, sometimes too warm, but still something you can walk under, sit in, or avoid with a bit of shade and a well-timed cloud. Think about a sunny day for a moment. Not an extreme one, just an ordinary afternoon. You step outside and within seconds you can feel the sunlight on your skin. It's gentle at first, maybe even pleasant. Give it a bit more time and it becomes something you notice more clearly. Stay out long enough and it starts to feel intense. Already, without moving an inch closer to the sun itself, you're experiencing a gradient, a range of effects, all controlled by distance, atmosphere, and exposure. But here's the interesting part. That sunlight has travelled about 150 million kilometres to reach you. That's the average distance between Earth and the Sun, often called an astronomical unit. And despite that enormous gap, the energy arriving here is still strong enough to warm oceans, power weather systems, and sustain life. So the question quietly starts forming. If it's this noticeable from so far away, what happens as you begin to close that distance? To answer that, we need to let go of one small assumption that tends to sneak in without us noticing. The idea that space, especially between planets, is cold. It's a reasonable guess. Space is often described as freezing, empty, and dark, and in many ways, it is. But temperature in space doesn't behave the way it does on Earth. On Earth, heat moves through air, water, and solid materials. You feel warmth, because molecules bump into each other and transfer energy. In space, there's almost nothing to carry that kind of heat. So even if you're very close to something extremely hot like the sun, the experience isn't quite what you might expect. Instead of being surrounded by hot air, you're exposed directly to radiation. Energy travelling in the form of light and other electromagnetic waves, and that changes everything. Imagine standing in direct sunlight, but without any atmosphere to soften it, no air to scatter the light, no ozone layer to filter out the more harmful radiation, no breeze to carry heat away from your skin, just pure, uninterrupted sunlight. That's much closer to what you'd experience in space. And already we're starting to approach the core of the question. Getting closer to the sun isn't just about distance, it's about exposure, about how much energy is hitting you, how quickly it builds up, and how your body, or any object for that matter, responds to it. But before we move too quickly toward the more extreme parts of this journey, it helps to take one more step back and think about scale. Because 150 million kilometers is a number that's easy to say and almost impossible to feel, so let's shrink it down. If the distance between Earth and the Sun were reduced to something more familiar, say 1 meter, then the Earth itself would be about the size of a tiny bead, just a few millimeters across. The Sun, on the other hand, would still be quite large, roughly the size of a big exercise ball. Even in this scaled-down version, the gap between them is still noticeable. You wouldn't accidentally bump into the Sun. You'd have to make a deliberate effort to move closer, and that's exactly what makes this question so interesting. Getting closer isn't just a matter of drifting inward. It requires overcoming motion, gravity, and a surprisingly tricky problem involving speed. Most people imagine that falling toward the Sun would be easy. After all, gravity is pulling everything inward, so you might expect objects to simply spiral down without much resistance. But in reality, Earth and everything on it is already moving sideways, orbiting the Sun at about 30 kilometers per second. That sideways motion is what keeps us from falling straight in. To actually move closer, you'd need to cancel out a significant portion of that speed. Not by speeding up, but by slowing down in a very precise way, and that turns out to be one of the most challenging parts of sending anything toward the Sun. It's a bit like trying to drop something straight down while you're already moving very fast sideways. You can't just let go and expect it to fall where you want. You have to carefully adjust your motion first, and that brings us to an interesting detail. Getting closer to the Sun is, in some ways, harder than leaving the solar system entirely. Escaping outward requires speed, but falling inward requires control. Now, while engineers and scientists have been working on this problem for decades, there is one spacecraft that has managed to get closer to the Sun than anything else humanity has ever built. We'll spend more time with it later, but for now, it's enough to know that even our most advanced technology approaches the Sun carefully, slowly, and with a great deal of protection. Because as you move inward, the increase in energy isn't gradual in the way you might expect. It rises quickly. Double the intensity, then triple it, then much more. Each step closer doesn't just feel slightly warmer, it becomes a completely different environment. At the distance of Mercury, the closest planet to the Sun, sunlight is already about 7 times more intense than it is on Earth. And even Mercury, a planet made of rock and metal, experiences extreme temperature swings because of that exposure. On the side facing the Sun, temperatures can climb high enough to melt certain metals. On the side facing away, they drop dramatically because there's no atmosphere to hold heat. So even before reaching anything resembling the Sun itself, you're already in a place where survival becomes very difficult. But something interesting happens here, and it's worth pausing on. Despite all this intensity, Mercury doesn't simply melt into nothing. It still exists. It still holds its shape, orbits steadily, and continues its quiet journey around the Sun. Which tells us something important. Getting closer to the Sun doesn't mean instant destruction. It means entering a new balance, one where materials, energy, and motion interact in ways that are harsher, but still governed by the same physical laws. And that idea will follow us as we continue moving inward. Because the Sun, despite how it appears in the sky, isn't a solid object waiting to be touched. It doesn't have a surface you can land on. Instead, it gradually transitions from a diffuse outer atmosphere into denser, hotter layers. So when we ask how close you could get, we're really asking how far into that environment you could go before something fundamental breaks down, before materials fail, before energy overwhelms structure, before the idea of being there stops making sense. And that's where things start to become both more complex and, in a quiet way, more fascinating. because the closer you get, the less the sun behaves like something familiar, and the more it becomes a process rather than a place. But we'll take our time getting there. For now, just hold on to the image of standing under sunlight, feeling its warmth and realizing that what you're experiencing is only a tiny fraction of what exists out there. A distant hint of something much more intense. A moment ago, we left ourselves standing somewhere familiar. Not in space, not near any spacecraft, but simply here, on Earth, noticing something easy to overlook. The warmth on your skin, the quiet presence of sunlight that doesn't ask for attention, but is always there when you step into it. Now, instead of rushing closer to the sun, it helps to stay right here for a little while longer and ask a simple question. What is that feeling exactly? When you say something feels warm, what's actually happening? Because the answer to that turns out to be the beginning of everything that follows. If you hold your hand out during the day, even with your eyes closed, you can often tell when sunlight is touching it. There's a subtle shift. Not dramatic, not overwhelming, just a gentle change that builds over a few seconds. At first it's barely noticeable. Then slowly your skin begins to register it more clearly. A quiet increase in energy. A steady presence. That sensation doesn't come from hot air. It doesn't travel through the breeze or rise up from the ground. It arrives directly from the sun itself, crossing the empty space between here and there without needing anything in between. That alone is a strange idea if you stop and think about it, because most of the warmth you feel in everyday life depends on contact. A hot cup warms your hands because it touches them. Warm air heats your skin because it surrounds you. Even standing near a fire, you're often feeling both the heated air and the radiation from the flames. But sunlight behaves differently. It doesn't need to touch you in the usual sense. Instead, it travels as energy in the form of electromagnetic radiation. A stream of photons, tiny packets of energy, moving at the speed of light. They leave the surface of the sun and spend about 8 minutes crossing the vast distance to Earth, arriving quietly, continuously, without interruption. And when they reach your skin, they don't bounce off entirely. Some of them are absorbed. That absorption is what you feel as warmth. It's a simple process on the surface, but it carries an interesting implication. The warmth you feel isn't something being transferred through air or carried by a medium. It's the direct result of energy arriving from a star that is unimaginably far away. In other words, even now, without going anywhere, the sun is already interacting with you. Not metaphorically, physically. That interaction is constant. It doesn't wait for you to notice it. It doesn't increase just because you think about it. It's happening all the time, quietly shaping the temperature of your surroundings, the climate of the planet, and even the way your body regulates itself. So when we ask how close you could get to the sun, we're not starting from zero. We're starting from a baseline where you're already within its reach. The question becomes less about first contact and more about how that contact changes as distance decreases. Now, to understand that change, we need to look at how energy spreads out. Imagine placing a small light source in a dark room. Close to the bulb, the light is bright and concentrated. Move farther away, and it becomes dimmer. Not because the bulb is producing less light, but because that light is spreading out over a larger area. The same thing happens with the sun, just on a much larger scale. At the distance of Earth, the sunlight is spread out enough that it feels manageable. Warm, sometimes strong, but still within the range where life can exist comfortably. If you were to move closer, that same amount of energy would be concentrated into a smaller area. The intensity would increase, not slowly, but quite quickly. This follows what's known as the inverse square law, although we won't dwell on the name. The important idea is simple. If you halve the distance to the sun, the intensity of sunlight doesn't just double, it becomes 4 times stronger. Move even closer, and the increase becomes more dramatic. That's why the difference between Earth and Mercury isn't just a small step toward more warmth. It's a shift into a completely different environment. But before we go that far, it's worth noticing something subtle about how your body experiences this energy. Because the warmth you feel isn't just about how much energy is arriving, it's also about how quickly your body can respond to it. Your skin absorbs some of the incoming radiation, converting it into heat. That heat raises the temperature of the surface of your body, which is then carried away by blood flow, air movement, and various internal processes. In other words, your body is constantly balancing energy coming in with energy going out. As long as that balance is maintained, the warmth feels comfortable, maybe even pleasant. But if the incoming energy starts to exceed what your body can handle, that's when things change. The warmth becomes intense, then uncomfortable, then potentially harmful. And that transition can happen more quickly than you might expect. Think about a hot summer day. Not an extreme one, just a day where the sun feels strong. You step outside, and after a while you start to feel overheated. Not because the sun suddenly changed, but because your body is reaching its limits in managing the incoming energy. Now imagine increasing that energy several times over. No atmosphere to filter it, no clouds to soften it, no shade unless you bring it with you. Just direct exposure. At that point, the feeling of warmth stops being something gentle and becomes something much more immediate. But we're not there yet, because there's another important factor that shapes how the sun touches you, and it has to do with Earth itself. Our planet isn't just sitting passively in sunlight, it actively modifies what reaches the surface. The atmosphere plays a crucial role here. It scatters some wavelengths of light, absorbs others, and reflects a portion back into space. That's why the sky appears blue, why sunsets are red, and why the sunlight that reaches you isn't exactly the same as what left the sun. Without this filtering, the experience of sunlight would be very different. More intense, more direct, and more dangerous over long periods. The ozone layer, for example, absorbs a significant portion of ultraviolet radiation. Without it, even short exposure to sunlight would have much more severe effects on your skin and eyes. So part of what makes sunlight feel manageable on Earth is the presence of this protective layer. It softens the interaction. It turns something potentially overwhelming into something livable. And this is where the idea of distance starts to intertwine with the idea of protection. Because moving closer to the sun isn't just about reducing the gap between you and it. It's also about leaving behind the layers that currently shield you. The atmosphere, the magnetic field, even the position of Earth itself, all of these contribute to how sunlight is experienced. Take them away, and the same sunlight becomes something else entirely. Astronauts, for instance, experience sunlight differently when they're in orbit. Without the full protection of the atmosphere, the light is sharper, more direct, shadows become deeper, the contrast increases, and while they are still at roughly the same distance from the sun as we are on the surface, the absence of atmospheric filtering changes the experience noticeably, so even small changes in environment can alter how the sun feels. Which brings us back to the central idea. The sun doesn't need to be close to affect you. It already does. The warmth on your skin is evidence of that. A quiet reminder that distance in space doesn't mean absence of influence. In fact, in many ways, the sun is one of the most present things in your life, even when you're not looking at it. It drives weather patterns, ocean currents, plant growth, and the cycles of day and night. It influences your sleep, your mood, and even the way your body keeps time. All of that from a distance that feels almost abstract when expressed in numbers. So when we begin to imagine moving closer, we're not introducing a new interaction, we're amplifying an existing one, turning up something that is already there, and that shift from gentle warmth to overwhelming intensity is not just a matter of stepping forward, it's a progression that builds, layer by layer, as energy becomes harder to ignore and more difficult to manage. Take a moment, just briefly, to imagine looking up at the sun. Not directly, of course. Even the thought of that comes with a quiet warning built into it. You already know, without needing to be told that it's too bright, too intense to stare at safely. So instead, picture it the way you usually notice it: a glow behind your eyelids, a strong presence in the sky, a source of light that fills everything else rather than something you examine directly. Even from this distance, it's not something you casually observe, it's something you work around. And that alone is interesting, because most objects in the sky, the moon, stars, even distant planets, invite observation. You can look at them, study them, take your time. The sun doesn't quite allow that. It dominates your vision to the point where your eyes instinctively turn away. So what is it that you're actually seeing? At first glance, it seems simple: a bright, circular disk, smooth, uniform, almost featureless unless you're using special equipment. It looks solid, like a glowing coin placed against the sky. But that impression is a bit misleading, because the sun isn't a solid object in the way a planet is. It doesn't have a surface you could stand on, or even clearly define in the way you might expect. What you're seeing is something closer to a boundary, a region where light is finally able to escape freely into space. That region is called the photosphere. The name sounds technical, but the idea behind it is straightforward. It's the layer of the sun from which most of the visible light is emitted. Not the centre, not the deepest part, but the outermost layer that appears opaque to us. Opaque in this case means that light from deeper inside can't pass through easily. Instead, it gets absorbed, scattered, and re-emitted over and over again, until eventually it reaches this outer layer and escapes. So when you look at the sun, you're not seeing into it. You're seeing the point where it becomes visible. That distinction matters more than it might seem at first, because it means that what appears to be a surface is actually just a transition zone, a place where the sun changes from something that traps light to something that releases it. If you could somehow move closer, safely and gradually, the sun wouldn't suddenly become a solid object. It would become brighter, more detailed, more dynamic, but still not something you could land on. Instead of a smooth disk, you'd begin to notice texture. The photosphere isn't perfectly uniform. It's covered in patterns called granules, which are essentially the tops of enormous convection cells. Hot plasma rises from below, cools slightly as it radiates energy into space, and then sinks back down, creating a constantly shifting surface. These granules are huge. Each one can be about the size of a country, but from Earth, at this distance, they blend together into what looks like a smooth glow. So even the simplest image of the sun, that bright circle in the sky, is hiding a lot of complexity, and that complexity increases the closer you get. But before we move inward, there's another detail worth considering: the colour of the sun. If you've ever drawn it as a child, you probably coloured it yellow, maybe orange, especially during a sunset. But in reality, the sun is closer to white. The reason it appears yellow from Earth has to do with the atmosphere again. Shorter wavelengths of light, like blue, are scattered more easily, leaving the direct sunlight that reaches your eyes slightly shifted toward yellow and red. Outside the atmosphere in space, the sun would appear much whiter, more neutral. Which is another reminder that what you see from here is always influenced by where you're standing. Your view of the sun is shaped by the air above you, the angle of the light, even the time of day. Morning and evening sunlight passes through more of the atmosphere, scattering more blue light and leaving behind those warm orange and red tones. At midday, when the sun is higher, the light travels a shorter path through the atmosphere, and the colour appears brighter, closer to white. So the sun doesn't actually change colour. Your perspective changes, and this idea will keep returning as we move forward. Because getting closer to the sun isn't just about reducing distance. It's about stripping away layers of interpretation. Atmosphere, scattering, filtering, all of it gradually disappears, leaving a more direct, less forgiving view. Now, there's one more aspect of looking at the sun that often goes unnoticed: the fact that the light you see is not immediate. When you look up, you're seeing the sun as it was about 8 minutes ago. That's how long it takes for light to travel from the sun to Earth. 8 minutes doesn't sound like much, but it introduces a subtle delay into everything you see. If the sun were to change suddenly, hypothetically, you wouldn't know right away. The information would take time to reach you, so even the simple act of looking up is, in a way, looking slightly into the past. It's a small detail, but it adds another layer to the idea of what you're actually observing. You're not just seeing the sun, you're seeing a version of it that has already happened. Now, as we start to imagine moving closer, that delay becomes shorter. The light has less distance to travel, so what you see becomes more immediate. But something else happens too. The brightness increases, not just in intensity, but in a way that begins to overwhelm your ability to process it. From Earth, the sun is already bright enough to be uncomfortable to look at directly. That's because your eyes are sensitive, and the amount of light entering them exceeds what they can handle safely. As you move closer, that brightness increases rapidly. Not in a gradual, easy-to-adjust way, but in a way that quickly becomes unmanageable without protection. This is why spacecraft designed to approach the sun don't rely on cameras in the way you might expect. They use specialized instruments, filters and shields to manage the incoming radiation. Because seeing the sun up close isn't just about clarity. It's about survival. Your eyes, like the rest of your body, are not designed to handle that level of exposure. And this brings us back to the idea of what seeing really means in this context. From Earth, you see a softened version of the sun, filtered by atmosphere, moderated by distance, adjusted by your own biology. It's bright, yes, but still within a range that your environment helps you tolerate. Remove those filters, and the experience changes completely. The sun doesn't become more detailed in a comfortable way. It becomes overwhelming. Light stops being something you observe and becomes something you endure. And that transition happens much sooner than most people expect. But even with all this in mind, there's still something deceptively simple about the way the sun appears from here. A circle in the sky, predictable, consistent, always rising, always setting. It gives the impression of stability, and in many ways it is stable. The sun has been shining for billions of years and will continue to do so for billions more. But the surface you see, that photosphere, is anything but still. It's constantly in motion, boiling, shifting, releasing energy in ways that are difficult to imagine on a human scale. Solar flares, for example, are sudden releases of energy that can outshine entire regions of the sun for brief periods. They send bursts of radiation and charged particles into space, sometimes reaching Earth and interacting with our magnetic field. From here, those events are often invisible without instruments, but closer in, they would be impossible to ignore. The sun isn't just a source of steady light. It's active, dynamic, unpredictable in small ways, even if it remains stable overall. And that activity becomes more apparent the closer you get. Which brings us to an important shift in perspective. Up to now, we've been thinking of the sun as something you look at from a distance, a bright object in the sky. But as we continue moving inward, that idea starts to break down. The sun stops being a distant object and starts becoming an environment, not something you observe, but something you enter, and once you begin to enter it, the question of what you see becomes less important than the question of what you experience, because at that point, light, heat, and radiation are no longer just things you notice. They're conditions you exist within. And that change from observer to participant is where the journey really begins to shift. At a glance, the sun doesn't feel far away. It sits there in the sky, always in roughly the same place, rising and setting with quiet consistency, almost like it's part of the local environment rather than something distant. You don't need a telescope to notice it. You don't need to search the sky. It simply shows up every day as if it belongs nearby. And because of that familiarity, your mind does something subtle. It compresses the distance. It turns something vast into something manageable, something that feels almost reachable, at least in imagination. After all, when you look at mountains on the horizon, they feel far, but still within the world you move through. The sun, in a strange way, can feel similar, present, visible, part of your daily surroundings. But this is where intuition quietly stops being reliable, because the actual distance between you and the sun is not just large. It's so large that ordinary comparisons start to break down. About 150 million kilometers separate Earth from the sun. It's a number that's easy to say and nearly impossible to feel. If you tried to drive that distance at highway speed, say around 100 kilometers per hour, without stopping, without sleeping, it would take you over 170 years to get there. Not a journey, but a lifetime stretched far beyond what most people experience. Even light, the fastest thing we know, takes about 8 minutes to make the trip. That's how far away the sun really is. And yet, it doesn't feel that way, because your senses aren't built to understand scale on that level. They're built for rooms, landscapes, distances you can walk, maybe fly across in a few hours. Beyond that, the mind starts to simplify. It turns millions into very far, billions into even farther, and anything beyond that becomes abstract. So the sun, despite being vastly distant, becomes something familiar instead of something remote. Now, here's where things start to become interesting. Because while the number itself is difficult to grasp, the consequences of that distance are much easier to notice. The sunlight that reaches you has spread out across that entire space. By the time it arrives, it's diluted enough to feel gentle, at least most of the time, warm, not overwhelming, bright but still manageable with a bit of caution. That's the version of the sun you know. But what happens if you begin to reduce that distance? Not by imagining the number shrinking, but by thinking about what changes as you move closer. The first thing to understand is that the sun doesn't get a little bit stronger as you approach. It gets stronger quickly. Because the energy it emits spreads out in all directions, like light from a bulb, but on a much larger scale. As you move closer, you're stepping into a region where that same amount of energy is concentrated into a smaller and smaller space. And that concentration increases in a way that isn't intuitive. If you were to cut the distance between you and the sun in half, the intensity of the sunlight wouldn't just double, it would become 4 times stronger. Cut the distance again, and it increases again by the same factor. So the journey inward isn't linear. Each step closer changes the environment more dramatically than the last. This is why the distance matters so much. It's not just a number, it's a buffer, a protective gap that allows the energy of the sun to spread out before it reaches you. Remove that gap and everything changes. But before we move inward, it helps to anchor this distance in something a bit more tangible. Imagine placing the sun and Earth on a scale you can actually see. If the sun were about the size of a large ball, something like 1 meter across, then Earth would be roughly the size of a small marble. Not just smaller, but much smaller than most people expect. And the distance between them, even on this scale, would still be about 100 meters. That's the length of a football field. So even when you shrink everything down to something manageable, the separation remains significant. You wouldn't stand next to the sun. You'd have to walk quite a distance just to reach the space where Earth would be. And that's important because it highlights something easy to overlook. The solar system is mostly empty. Not empty in the sense of having nothing in it, but empty in the sense that the objects within it are separated by vast stretches of space. So when we talk about moving closer to the sun, we're not talking about stepping forward a few paces. We're talking about crossing a region where the environment changes gradually at first, and then more rapidly as you approach. And here's where another subtle misconception comes in. It's easy to imagine that moving closer to the sun would feel like walking toward a fire. You step forward, and it gets warmer. Step again. Warmer still. But space doesn't behave like that. There's no air to carry heat. No gradual warming of the environment around you. Instead, the change is in the radiation itself. The energy arriving directly from the sun increases, but the space between remains largely the same. So the experience isn't of moving through hotter and hotter air, it's of being exposed to more and more intense energy. That difference matters, because it means there's no gentle transition, no warning in the form of warmer surroundings, just an increasing intensity that becomes noticeable once it crosses a certain threshold. Now consider where we are right now. At Earth's distance, the balance between incoming solar energy and the planet's ability to distribute and radiate that energy back into space creates a stable environment. Temperatures vary, weather shifts, but overall, conditions remain within a range that supports life. That balance is delicate. Move slightly closer, and the average temperature increases. Move farther away, and it decreases. Even small changes can have large effects over time, and this is where the idea of distance becomes more than just a measurement. It becomes a condition, a specific position where things happen to work out in a particular way. Earth sits in a region where the sun's energy is neither too weak nor too strong, a narrow band, sometimes called the habitable zone. And while we won't dwell on that concept too much, it's worth noting that this position isn't arbitrary. It's part of what makes the environment you're familiar with possible. Shift that position inward, and the balance begins to change, gradually at first, then more dramatically. Now, if we start imagining a journey toward the sun, one that begins here and moves inward, the first part of that journey would feel surprisingly uneventful. You'd leave Earth, move into space, and for a while, not much would seem different. The sun would grow slightly larger in the sky, a bit brighter, but not drastically so. Because over large distances, small movements don't produce dramatic changes. But as you continue, that begins to shift. The sun's apparent size increases more noticeably, the brightness intensifies, and the energy reaching you starts to climb in a way that becomes harder to ignore. By the time you reach the orbit of Mercury, things are already very different. The sun appears much larger in the sky, several times its size as seen from Earth. The light is harsher, more direct. The energy is stronger by a significant factor, and yet, even there, you're still not close in the way most people imagine. You're closer, yes, but still separated by tens of millions of kilometers, which tells you something important. The sun's influence extends far beyond what feels intuitive. Even at what we consider a safe distance, it's already shaping everything. And as you move inward, that influence becomes more concentrated, more immediate, but never sudden in the way you might expect. There's no clear boundary where things change from safe to unsafe. Instead, it's a gradient, a continuous increase, and that makes the question of how close could you get more nuanced than it first appears. Because there isn't a single line you cross. There are many thresholds, points where different materials begin to fail, where different systems stop functioning, where the environment becomes incompatible with survival in one way or another, and those thresholds don't all occur at the same distance. Some happen far out, others much closer in. So the journey toward the sun isn't about reaching a single point. It's about passing through a series of conditions, each more demanding than the last, and all of them shaped by that initial distance. That 150 million kilometer gap that feels small when you look at the sky, but turns out to be doing a lot of work behind the scenes, holding everything in a kind of balance, softening what would otherwise be overwhelming. Instead of moving closer right away, it helps to begin by stepping away. Not in a dramatic way, not all at once, but slowly, as if you were lifting yourself upward, leaving behind the ground beneath your feet, the air around you, and all the familiar signals that quietly define what normal feels like. Because before you can understand what it means to approach the sun, you need to understand what it means to leave Earth, and that turns out to be a much bigger shift than most people expect. At first, nothing seems to change very much. If you were rising gently above the surface, the sun would still look the same. Bright, steady, sitting in the sky as it always does. The warmth on your skin would still be there. The light's still surrounding you, the same quiet presence you've known your entire life. But as you continue upward, something subtle begins to fade. The air. It doesn't disappear all at once. It thins gradually. The pressure drops, the sky begins to darken, and the familiar blue starts to lose its colour. That blue, the one you've probably never questioned, isn't actually the colour of space. It's the result of sunlight scattering through the atmosphere, bouncing off molecules in the air in a way that favours shorter wavelengths. Remove the air, and the blue goes with it. So as you climb higher, the sky shifts, from bright blue to a deeper shade, then to something almost black, even while the sun is still shining just as strongly as before. That's one of the first quiet surprises. The sun doesn't need a blue sky to exist. The blue sky needs the sun, and without the atmosphere, you begin to see things a little more directly. Now, as the air continues to thin, another familiar sensation begins to change. The way warmth feels. On the surface of Earth, warmth is something that surrounds you. The air carries it, the ground holds it, and your body exchanges heat with everything around you. In space, that connection is gone. There's no air to carry heat away from your skin or toward it. No breeze, no convection, no gentle mixing of temperatures. Instead, you're left with radiation. Direct, unfiltered energy from the sun, arriving in a steady stream. If you were exposed to it without protection, the side of you facing the sun would begin to heat up, while the side facing away would remain much cooler. That contrast can be surprisingly sharp. Because in space, temperature isn't something that spreads evenly. It depends almost entirely on what you're exposed to and what you're touching. So even before you begin moving closer to the sun, simply leaving Earth changes how you experience it. The same sunlight, but a different environment. The same energy, but a different interaction. Now, let's continue the journey. As you move farther from the surface, leaving behind even the highest layers of the atmosphere, Earth begins to shrink beneath you. At first, it's still large, still detailed. You can make out continents, oceans, cloud patterns shifting slowly across the surface, but over time it becomes smaller, more distant, eventually turning into something that resembles the images you've seen. A sphere suspended in darkness, bright against the black background of space. And in that moment, something else becomes more noticeable, the sun's position relative to everything else. On Earth, the sun defines your day. It rises, sets, moves across the sky in a way that feels tied to your location. In space, that sense of movement changes. The sun becomes a fixed point, not because it has stopped moving, but because your frame of reference has changed. You're no longer anchored to the rotating surface of a planet. You're moving independently, and that changes how everything appears. The sun is still there, still bright, but now it's part of a much larger scene. A scene where distances are harder to judge, where objects don't move in familiar ways, and where your intuition starts to lose its footing. Now here's something that often surprises people. Leaving Earth doesn't immediately make you feel closer to the sun. In fact, for a while, it can feel almost the same. Because the scale of the solar system is so large that even significant distances, by human standards, don't change your position relative to the sun very much. Low Earth orbit, for example, is only a few hundred kilometers above the surface. Even higher orbits, thousands of kilometers up, are still extremely close compared to the 150 million kilometers separating Earth from the sun. So in those early stages, the sun doesn't grow dramatically larger. It doesn't suddenly become overwhelming. It remains familiar, and that familiarity can be misleading, because it suggests that moving through space is a simple extension of what you already know. But the reality is a bit more complicated. To truly leave Earth, to move beyond its gravitational influence in a meaningful way, you need to reach a certain speed. Not just any speed, but what's known as escape velocity. For Earth, that's about 11 kilometers per second. That's fast enough that once you reach it, you're no longer bound to fall back to the surface. You can continue moving outward, away from the planet into the wider solar system. But here's where things become interesting. Even after you escape Earth, you're still moving around the Sun, because Earth itself is orbiting the Sun at about 30 kilometers per second, and anything leaving Earth carries that motion with it. So instead of drifting straight outward, you're now part of a larger system. You've left Earth, but you haven't left the Sun's influence. And that's an important distinction, because it means that the journey toward the Sun isn't just about getting closer in a straight line, it's about changing your motion relative to that larger system. But before we go further into that, it's worth pausing on what this transition feels like conceptually. Leaving Earth is not just a change in location, it's change in context. On Earth, everything is grounded, up and down have meaning, temperature behaves in familiar ways. The sky provides a backdrop that feels constant. In space, those references disappear. There's no up or down in the usual sense, no atmosphere to scatter light, no environment to smooth out extremes. Instead, you're in a place where the rules are the same, but the conditions are very different, and that difference becomes more noticeable the farther you go. Now, as you continue moving outward, away from Earth's immediate surroundings, the planet becomes smaller still. Eventually it turns into a bright point among others, and at that stage something subtle begins to shift in how you perceive distance. Objects that once felt large and close now feel small and far. The scale of everything changes, and in that new scale, the Sun begins to stand out more clearly as the dominant presence. Not just a light in the sky, but the central anchor of everything around you. The source of gravity that shapes the orbits of planets, the source of energy that drives the entire system. And even though you've been aware of that all along, seeing it from this perspective makes it feel more immediate, more real. Now, here's where the journey begins to turn, because up to this point, we've been moving away from Earth, adjusting to the idea of space, noticing how the environment changes as you leave the surface behind. But the question we started with isn't about moving away, it's about moving closer, and to do that you don't simply continue in the same direction, you need to change course. Not by accelerating forward, but by doing something that feels counterintuitive. You need to slow down relative to the Sun. Because as long as you're moving sideways fast enough, you'll continue orbiting, circling around at a distance. To fall inward, to actually begin closing the gap, you have to reduce that sideways motion, and that turns out to be one of the most challenging parts of the entire journey. It's not about pointing yourself at the Sun and going faster, it's about carefully adjusting your path so that you begin to spiral inward instead of continuing around. And that shift, from orbiting to approaching, is where the experience starts to change more noticeably. Because once you begin that inward movement, even slowly, the Sun doesn't just remain a distant light. It starts to grow. Not suddenly, not dramatically at first, but enough that you begin to notice. A slightly larger disk, a slightly brighter presence, a gradual increase in intensity, and with that increase comes the next set of changes, not just in what you see, but in what you feel, what you experience, and what becomes possible or impossible as you continue moving closer. Once you've left Earth behind and allowed yourself to settle into the idea of open space, something quiet but important begins to shift in how you think about it. At first, space is often imagined as empty, cold, dark, and completely still. A kind of vast nothingness, where nothing really happens unless something moves through it. It's a simple picture, and in some ways it's understandable. After all, compared to Earth, space does feel empty. There's no air, no weather, no familiar textures or sounds. But empty turns out to be a bit misleading. Because even in the spaces between planets, there's still a presence. Not something you can see in the usual sense, not something you can touch directly, but something that becomes more noticeable the more you think about it. Energy. Even far from any planet, even in regions where there's almost no matter at all, the Sun is still there. sending out a continuous flow of light and radiation in every direction. That flow doesn't stop just because there's nothing in the way. In fact, the absence of obstacles means it travels freely, uninterrupted, spreading outward across the entire solar system. So while space may be mostly empty of material, it's not empty of influence. And that influence becomes the dominant feature of the environment the moment you leave Earth behind. Now, earlier we touched on the idea that heat in space doesn't behave the way it does on Earth. There's no air to carry warmth, no medium to distribute it evenly. That means temperature, as a concept, becomes less intuitive. In everyday life, you can step from a warm room into a cooler one and immediately feel the difference. That's because your body is exchanging heat with the air around you. In space, that exchange works differently. Without air, there's nothing to conduct or convect heat in the usual way. Instead, energy arrives primarily through radiation, and that means your experience of warmth depends almost entirely on what you're exposed to. If you're facing the sun, you're receiving energy directly. If you're turned away, you're not. That contrast can create situations that feel almost contradictory. The side of an object facing the sun can become very hot, while the shaded side remains extremely cold. Not because space itself is cold in the way we usually think of it, but because there's very little to balance things out. So rather than a uniform temperature, you get extremes, localized, directional, dependent on exposure. This is one of the first ways in which space reveals that it isn't truly empty. It's filled with gradients, differences in energy that become more noticeable the farther you move from the buffered environment of Earth. Now, there's another layer to this, because the sun isn't just emitting visible light, it's also releasing a constant stream of charged particles, known as the solar wind. This wind isn't something you'd feel in the way you feel air moving across your skin. It's far too sparse for that. But it's still there, flowing outward, carrying energy and magnetic fields across the solar system. Earth is protected from most of this by its magnetic field, which deflects many of these particles and channels, some of them toward the poles, where they create phenomena like the auroras. But once you move away from that protection, you're exposed more directly. Again, not in a way that feels like a gust of wind, but in a way that becomes significant over time, especially for anything that remains in space for long periods. So space, even in its quietest regions, is not static. It's active. Subtle, yes, but constantly influenced by what the sun is sending outward. And that influence becomes more important as you begin to move closer, because the density of that energy, both in the form of radiation and particles, increases, gradually at first, then more noticeably. But before we move too far inward, it's worth considering how this subtle environment affects objects. Take a spacecraft, for example. If you place it in space, far from any planet, it doesn't simply float in a neutral environment. It's continuously interacting with sunlight. The side facing the sun absorbs energy, heating up. The side facing away loses energy, cooling down. Without careful design, this can create large temperature differences across the structure. That's why spacecraft often have reflective surfaces, insulation, and rotating components. Not because space is inherently hot or cold, but because it's uneven. And managing that unevenness becomes essential. Now think about this in terms of the journey toward the sun. At Earth's distance, the amount of energy arriving from the sun is something your environment can handle. The atmosphere distributes it, the oceans absorb and release it, and your body regulates itself within that system. As you move closer, those buffers disappear. There's no atmosphere to scatter light, no environment to smooth out temperature differences. So the same principles still apply, but the consequences become more immediate, more direct, and that's where the idea of subtle heat becomes more noticeable. Because even in regions that might seem empty, the sun's influence is already present. It's just that at greater distances it's diluted, spread out, easy to ignore unless you're paying attention. But as you begin to close that distance, the subtle becomes less subtle, the gradients become steeper, the differences more pronounced, and the environment begins to feel less like empty space and more like an extension of the sun itself. Now, there's another interesting aspect to this, because while we often think of space as cold, that description is based on the idea of temperature as an average. If you measure the average temperature of space, it's indeed very low, just a few degrees above absolute zero. But that average doesn't capture the experience of being exposed to direct sunlight. An object in sunlight, even in deep space, can become quite warm. In fact, satellites orbiting Earth can experience significant heating on their sunlit sides, even though they're surrounded by what we call the cold vacuum of space. So the coldness of space is not something you feel directly in the presence of the sun. It's something that becomes apparent when you're not exposed to any source of radiation. And this duality, the coexistence of intense heat and extreme cold, is one of the defining features of space. It's not one or the other, it's both, depending on where you are and what you're facing. Now, as we continue this journey inward, this balance begins to shift. The cold side remains cold, but the hot side becomes hotter. The energy arriving from the sun increases, and with it the demands on anything trying to exist in that environment. But importantly, this change doesn't happen all at once. It builds. And because it builds, it allows for a gradual transition in how conditions evolve. At first, the differences are manageable. Then they require careful design and protection. Eventually, they become limiting factors that determine what is possible and what is not. And this is where the idea of how close could you get starts to take on more structure. Because the answer isn't a single point. It's a series of thresholds, distances at which different materials, systems, and even concepts begin to fail. And those thresholds are shaped by this very environment. An environment that, while appearing empty, is quietly filled with energy, particles, and interactions that become more intense the closer you move toward their source. So even here, in what might seem like the quiet middle ground between worlds, the sun is already present, already shaping the conditions. Now the journey begins to feel different. Up until this point, moving through space has been more of a shift in perspective than a change in conditions. Earth fades behind you, the sun grows slightly larger, and the environment becomes quieter, more direct, less filtered. But nothing has felt overwhelming yet. Nothing has crossed that threshold where the sun stops being familiar and starts becoming something else. That change begins here. Because approaching Mercury is the first time the sun's presence stops feeling distant and starts becoming unavoidable. At this distance, the sun is no longer just a bright point in the sky. It begins to take up more space in your field of view. Not dramatically at first, but enough that you notice it without trying. Enough that it draws your attention even when you're not looking directly at it. And along with that visual change comes something more important: the intensity. At Mercury's orbit, the sunlight is about 6 to 7 times stronger than what you experience on Earth. That's not a small increase. It's the difference between something you can comfortably exist in and something that begins to demand constant awareness. If you imagine standing under sunlight on Earth, even on a very hot day, you still have options. Shade helps, clothing helps, air movement carries heat away. Your body can regulate itself for a while. Here, those options begin to disappear. There's no atmosphere to soften the light, no air to distribute heat, no natural buffer between you and the sun, just direct exposure. And because of that, the energy arriving at any surface facing the sun builds quickly, not instantly, not explosively, but steadily and relentlessly. An object exposed to sunlight at this distance begins to heat up much faster than it would on Earth. The equilibrium point, the balance between incoming and outgoing energy, shifts upward. Surfaces that would feel warm at Earth's distance now become hot. Surfaces that would feel hot become extremely hot, and materials that were once stable begin to approach their limits. Now, it's important to pause here and notice something. Mercury itself hasn't melted into nothing. It still exists. It still orbits the sun in a stable path. completing a full orbit roughly every 88 Earth days. It hasn't been destroyed by the intensity of sunlight, even though it sits much closer than Earth. But Mercury is not a simple case, because while it receives a huge amount of solar energy, it also lacks something crucial: an atmosphere. Without an atmosphere, there's nothing to distribute heat across the planet's surface. No air currents, no weather systems, no way to move energy from one place to another efficiently. So instead of having a uniform temperature, Mercury experiences extremes. On the side facing the Sun, temperatures can rise to around 430 degrees Celsius, hot enough to melt lead, hot enough that most familiar materials would begin to struggle. But on the side facing away from the Sun, temperatures can drop to around minus 180 degrees Celsius, a swing of more than 600 degrees between day and night. Not because the Sun is inconsistent, but because Mercury has no way to balance what it receives, and that tells you something important about approaching the Sun. It's not just about how much energy is coming in, it's also about what happens to that energy once it arrives. On Earth, the atmosphere, oceans and land all work together to distribute and moderate heat. On Mercury, that system doesn't exist, so the intensity of sunlight expresses itself more directly, more honestly, you might say. Now, as you imagine moving through this region somewhere near Mercury's orbit, the Sun's presence becomes more than just a background condition. It becomes the defining feature of the environment. The light is sharper, the shadows are darker. The contrast between exposed and shaded areas becomes more pronounced. And that contrast isn't just visual, it's physical. The difference between being in sunlight and being in shadow is no longer subtle, it's immediate. Now, consider what that means for anything trying to exist here. A spacecraft, for example, would need to manage this constant influx of energy very carefully. It would need reflective surfaces to reduce absorption, insulation to control internal temperatures, radiators to release excess heat, and perhaps most importantly it would need to maintain orientation, keeping its most sensitive components shielded from direct sunlight as much as possible. Because at this distance, even small design choices can have large consequences. Now, here's where things begin to feel less intuitive. Despite the intensity, being at Mercury's distance doesn't mean instant destruction. Objects don't simply vaporize the moment they enter this region. Instead, they heat up. They reach new equilibrium temperatures. They adapt if they're designed to do so. And that's because, even here, the energy is still arriving through radiation. There's no medium to trap heat around you. No surrounding environment that becomes hot in the way air does on Earth. So while the sunlight is intense, the absence of atmospheric trapping means that heat doesn't build up in quite the same way. That's why, for example, a spacecraft can survive near Mercury if it's designed properly. It doesn't need to withstand a surrounding sea of hot gas. It needs to manage the energy it absorbs, reflecting some, radiating away the rest. But this balance becomes harder to maintain the closer you get, because the incoming energy increases faster than your ability to deal with it, and Mercury is the first place where that increase becomes impossible to ignore. Now, let's shift perspective slightly. Instead of thinking about temperature, think about light. At this distance, the Sun appears much larger in the sky. From Mercury's surface, the Sun would look about 2.5 times wider than it does from Earth. And because brightness scales with area, it would also appear significantly brighter. Not just in a way that feels intense, but in a way that dominates everything else. The sky, if you could call it that, would be black, because there's no atmosphere to scatter light, but the Sun itself would be overwhelming, a brilliant disk too bright to look at directly, even more so than from Earth. And that visual dominance reinforces the idea that you're entering a different kind of environment, one where the Sun is no longer just a source of light, but the central presence that defines everything around you. Now, here's something else that becomes more noticeable at this distance. Time, not in the sense of clocks or schedules, but in the way conditions change. Mercury rotates very slowly. A single day, from sunrise to sunrise, lasts about 176 Earth days, which means that once the sun rises in a particular location, it stays in the sky for a very long time, and during that time, the surface continues to absorb energy, heating up gradually, reaching those extreme temperatures we mentioned earlier. Then, when the sun finally sets, the process reverses. The surface begins to lose heat, cooling down over time. But without an atmosphere to slow that cooling, it happens more directly, more efficiently, leading to those extreme nighttime temperatures. So even at this first major step inward, you begin to see how the sun's influence shapes not just temperature, but the entire rhythm of an environment. Now, as we continue to move closer, something important becomes clear. Mercury is not the endpoint. It's a marker, a place where the sun's intensity becomes undeniable, but still manageable under the right conditions. Beyond this point, the challenges increase, the energy rises, the environment becomes more demanding, and the question of how close you can get begins to depend less on distance alone and more on what you're made of, what you can withstand, what you can reflect, absorb, or survive. Something changes once you stop thinking of sunlight as warmth. Up to now, it has been easy to describe the sun in terms that feel familiar. Warmth on your skin, brightness in your eyes, a steady presence that grows stronger as you move closer. But those descriptions, while useful, are also a little incomplete, because what's arriving from the sun isn't really heat in the way you experience it on Earth. It's radiation. And that difference matters more than it might seem at first. If you place your hand near a hot surface, like a radiator or a stove, the warmth you feel comes partly from direct contact with heated air. Molecules moving faster, bumping into your skin, transferring energy in a way that feels immediate and surrounding. Sunlight doesn't work like that. There's no air carrying it, no medium delivering it gradually. Instead, energy travels through empty space as electromagnetic waves, crossing millions of kilometers without losing their direction, without spreading into a surrounding substance. And when that energy reaches you, it doesn't feel like heat at first. It becomes heat only after it interacts with matter. Your skin absorbs some of those incoming photons, and that absorbed energy increases the motion of molecules within your body. That increase in motion is what you interpret as warmth. So the warmth is not what arrives, it's what happens after arrival. Now, at Earth's distance, this process feels gentle, manageable. You step into sunlight, and the effect builds slowly. Your body has time to respond. Blood flow adjusts, sweat forms. You move into shade if needed. But as you move closer to the sun, something subtle but important begins to change. The rate at which that energy arrives. Not just a little faster, much faster. And because it arrives faster, your body, or any material, has less time to respond before the effects begin to accumulate. This is where the idea of burning starts to make sense. Because burning in this context isn't about flames, it's about energy arriving faster than it can be managed. Now, to understand this more clearly, it helps to look at what sunlight actually consists of. It's not just visible light. The light you can see, the part that makes things appear bright and colourful, is only a small portion of the full spectrum of radiation coming from the sun. Alongside it, there's infrared radiation, which carries a significant amount of energy and is strongly associated with heat, and there's ultraviolet radiation, which carries even more energy per photon and interacts with matter in ways that can be more disruptive. At Earth's distance, much of the most harmful ultraviolet radiation is filtered out by the atmosphere, particularly by the ozone layer. That's part of why sunlight feels manageable here. But once you move beyond that protection, the composition of sunlight changes, not because the sun is emitting something different, but because nothing is filtering it anymore. So the radiation reaching you becomes more complete, more direct, more intense across all wavelengths. And this is where the experience shifts, because now you're not just dealing with warmth, You're dealing with a full spectrum of energy, some of which interacts with matter in ways that are less forgiving. Ultraviolet radiation, for example, has enough energy to break chemical bonds. That's what leads to sunburn on Earth. Your skin cells absorb this radiation, and the energy disrupts their structure, triggering a response that results in redness, inflammation, and eventually repair. But at Earth's distance, this process happens slowly enough that your body can respond. Closer to the sun, that balance begins to change. The same processes occur, but faster. More energy, arriving more quickly, means more disruption in less time. And beyond a certain point, the rate of damage exceeds the rate of repair. Now, it's important not to jump straight to extremes. Even closer to the sun, things don't instantly fall apart. There's still a progression, still a range of conditions where different effects become noticeable. But what changes is how quickly those effects build. Now, consider an object exposed to sunlight in space. Without an atmosphere, without any filtering, it receives the full intensity of solar radiation. If it absorbs that energy, its temperature begins to rise. If it reflects some of that energy, the rise is slower. If it can radiate energy away efficiently, it can maintain a stable temperature. But as the intensity increases, that balance becomes harder to maintain, because the incoming energy grows faster than the ability to remove it. And this is where materials begin to face limits. Different materials respond differently to radiation. Some reflect well. Some absorb and re-radiate efficiently. Some degrade when exposed to certain wavelengths. So the question of how close you can get to the sun isn't just about distance. It's about how materials interact with radiation. Now imagine moving inward, past Mercury's orbit, where the intensity of sunlight continues to rise. The visible light becomes brighter, more overwhelming. The infrared component delivers more energy, increasing heating rates. The ultraviolet component becomes more significant, interacting more strongly with exposed surfaces. And all of this happens simultaneously. There's no separation. No way to experience one without the others. So when people talk about the sun burning something, what they're really describing is the combined effect of all these forms of radiation, energy arriving in multiple ways, each contributing to the overall impact. Now, here's something that often gets overlooked. Radiation doesn't need to be visible to have an effect. Infrared radiation, for example, is invisible to your eyes, but it carries a large portion of the sun's energy. Ultraviolet radiation is also invisible, but it plays a significant role in how sunlight interacts with matter. So the experience of being close to the sun isn't just about what you see, it's about what you don't see. Energy arriving in forms that don't produce a visual signal, but still contribute to heating, chemical changes, and material stress. Now, consider how this would feel if you were exposed to it directly. At first, you might notice the brightness, then the warmth. But as the intensity increases, those sensations would build quickly. Not gradually, not comfortably, but in a way that becomes difficult to ignore. Your skin would absorb more energy than it can dissipate. Temperatures would rise. The balance between incoming and outgoing energy would shift. And the process that begins as warmth would move towards something more intense. But again, it's not instantaneous. There's still a progression, and that progression is important because it means there are distances where exposure is difficult but not immediately destructive, distances where protection makes survival possible. And that's where engineering comes in, because while the human body has limits, materials can be designed to handle higher levels of radiation. Reflective coatings can reduce absorption, heat shields can manage incoming energy, systems can be designed to radiate excess heat away. And this is exactly what has allowed spacecraft to move closer to the sun than you might expect. They don't rely on resisting heat in the traditional sense, they rely on managing radiation, controlling how much is absorbed, how much is reflected, and how efficiently energy can be released. But even with those strategies, there are limits, because as you continue to move closer, the intensity keeps increasing. and eventually you reach a point where even the best materials begin to struggle, where the rate of energy arrival exceeds the capacity of any system to manage it effectively. Now there's another aspect to consider. Radiation doesn't just heat, it also carries momentum. Photons, despite having no mass, can exert pressure when they interact with surfaces. At Earth's distance, this pressure is extremely small, almost negligible, but closer to the Sun it becomes more noticeable. Still small compared to other forces, but present. And this adds another layer to the environment. Not just energy arriving, but a constant push. A subtle force that becomes part of the overall interaction between objects and sunlight. So as you move inward, the Sun's influence becomes more complete. Not just in terms of brightness or warmth, but in the full range of ways radiation interacts with matter, heating, chemical changes, pressure, all of it increasing together. And this is where the idea of just getting closer starts to break down. Because you're not just reducing distance, you're stepping into a region where multiple effects are increasing at the same time, each one manageable on its own at certain distances, but together becoming more challenging. Now, at this point in the journey, the Sun is no longer something you observe from afar. It's something you interact with continuously. Every surface, every material, every exposed part of anything you bring with you is responding to that radiation. And that response determines how close you can go, not just physically, but practically. Because survival, whether for a human or a machine, depends on maintaining balance. Managing incoming energy in a way that prevents runaway heating, structural failure, or other forms of breakdown, and that balance becomes harder to maintain the closer you move. At first glance, it seems like anything placed near the Sun should simply fail right away. The assumption is understandable. You picture something moving closer and closer, the light getting brighter, the heat building, and then, at some point, everything just gives in. Melts, burns, disappears. A quick and final outcome. But that's not actually what happens. In fact, one of the more surprising things about space travel is that objects don't melt instantly, even in environments that seem far beyond what they should be able to handle. And the reason for that comes back to something we've been building slowly, the difference between heat and radiation. Because in everyday life, when something gets very hot, it's usually surrounded by something else that's also hot. Air, flames, surfaces, all working together to transfer energy quickly and continuously. Near a fire, for example, you're not just receiving radiation, you're also surrounded by hot air that transfers energy through contact. That combination makes the experience intense and difficult to escape. In space, that surrounding layer doesn't exist. There's no hot air wrapping around an object, no medium continuously feeding it energy from all directions. Instead, energy arrives from one main direction, the Sun. And that changes everything. Because it means that how something behaves near the Sun depends less on being in a hot place, and more on how it handles incoming radiation. Now consider a simple object, something like a metal plate. If you place it in sunlight in space, it begins to absorb energy on the side facing the Sun. That energy increases the motion of its atoms, raising its temperature. But at the same time, that object is also radiating energy away. Every object above absolute zero emits infrared radiation. It's constantly releasing energy into its surroundings. So what you have is a balance. Energy coming in from the Sun, energy going out through radiation. If those two rates match, the object reaches a stable temperature. Not cold, not continuously heating up, but holding steady. And this is the key idea. Objects don't keep getting hotter forever. They reach equilibrium. Now, as you move closer to the Sun, the incoming energy increases, which means the equilibrium temperature also increases. But it still exists. There's still a point where incoming and outgoing energy balance, and that's why spacecraft don't instantly melt. They're not just absorbing energy without limit, they're managing it. Now, how do they do that? The first step is controlling how much energy they absorb in the first place. Not all materials absorb sunlight equally. Some reflect a large portion of it, others absorb most of it, A dark surface, for example, absorbs more energy and heats up more quickly. A reflective surface, on the other hand, sends a significant portion of that energy away before it can be absorbed. So one of the simplest strategies is to use materials that reflect as much incoming radiation as possible. Bright, polished, or specially coated surfaces that reduce absorption. That alone can make a significant difference. But reflection isn't enough on its own. Some energy will always be absorbed, and once it's inside the material, it has to go somewhere. That's where the second strategy comes in. Radiating heat away. Spacecraft are designed to release energy efficiently. They often have surfaces specifically intended to emit infrared radiation, allowing them to shed excess heat. In a way, they're constantly cooling themselves, not by using air or fluids, but by emitting energy directly into space. Now here's something that might seem counterintuitive. In space, radiating heat away is actually easier in some ways than it is on Earth, because there's no atmosphere to interfere, no surrounding air to slow down the process. Energy can leave directly, travelling away as radiation. So while space doesn't help you distribute heat, it does allow you to get rid of it efficiently, if you're designed for it. Now let's add another layer. Orientation. A spacecraft doesn't have to expose all of itself to the sun. It can control how it's positioned. By keeping sensitive components in shadow and directing the most resilient surfaces toward the sun, it can limit how much energy reaches critical systems. This is where heat shields come into play. Instead of trying to make the entire spacecraft withstand extreme conditions, engineers focus on protecting it from one direction, the direction of the sun. A heat shield acts as a barrier. It absorbs and reflects incoming radiation, keeping the rest of the spacecraft in its shadow. And because there's no air to carry heat around the edges, that shadow remains effective. The protected side stays much cooler than the exposed side. Now combine all of these strategies: reflection to reduce absorption, radiation to release excess energy, orientation to control exposure, shielding to protect sensitive areas, and you start to see why spacecraft don't simply melt. They're not passively enduring the environment, they're actively managing it. But even with all of this, there are still limits, because as you move closer to the sun, the incoming energy increases faster than your ability to deal with it. The equilibrium temperature rises. Materials that were stable at one distance become unstable at another. At some point, the balance can no longer be maintained, but that point is much closer to the sun than intuition might suggest. And that's what makes this whole question interesting, because it shows that survival near the sun isn't just about distance, it's about design, understanding how energy flows, how materials respond, and how to maintain that balance for as long as possible. Now, let's consider a real example. Modern spacecraft that approach the sun don't rely on guesswork. They're built with extremely careful consideration of these principles. Their outer layers are designed to handle intense radiation. Their internal systems are positioned in protected regions. Their trajectories are planned to manage exposure over time. And because of that, they can survive in environments that would seem impossible at first glance. Not indefinitely, not without limits, but long enough to gather data, to explore, to push closer than anything before them. Now, there's another subtle point worth noticing. Melting as a concept implies a transition, a material reaching a temperature where it changes state, solid becoming liquid. But for many materials, especially those used in spacecraft, failure doesn't always look like melting. It can be gradual degradation, structural weakening, changes in properties that affect performance. So when we talk about something not melting instantly, it doesn't mean it's unaffected. It means the process takes time determined by how well the system manages incoming energy, and that time is what allows exploration to happen. Because even in extreme environments, if you can maintain stability long enough, you can operate, you can observe, you can learn, and that's exactly what we've done. We've built machines that can approach the sun, not by resisting it in a brute force way, but by understanding it, by working within the rules of radiation and energy balance. Now, as we continue moving closer, the demands on those systems increase. The margin for error decreases, the intensity rises, and the question of how close becomes more precise. Not just a matter of distance, but of how long something can maintain that balance before it fails. Because eventually, no matter how well designed, every system has a limit, and the closer you get, the faster you approach it. Long before anything ever reached this part of the journey, there was a quiet assumption that getting truly close to the Sun simply wasn't practical. Not impossible in theory, perhaps, but far beyond what engineering could realistically handle. The combination of intense radiation, increasing energy, and the difficulty of adjusting a spacecraft's motion made the idea feel distant, something for equations and imagination, not for actual machines. And yet, over time, that assumption began to change. Not suddenly, not dramatically, but gradually, as technology improved and understanding deepened. Engineers began to realize that the challenge wasn't just about resisting the Sun, but about working carefully within the conditions it creates. That realization eventually led to something very specific, a spacecraft designed not just to observe the Sun from afar, but to move into its outer atmosphere. That spacecraft is the Parker Solar Probe. Now, the name itself carries a bit of history. It was named after Eugene Parker, a scientist who first proposed the existence of the solar wind in the 1950s. At the time, the idea that the Sun was constantly emitting a stream of particles into space was controversial. It took years before observations confirmed it, so naming a spacecraft after him, one that would travel directly into that environment, feels fitting. But what makes the Parker Solar Probe truly interesting isn't just its name or its destination, it's how it gets there. Because reaching the Sun is not like travelling to another planet. If you want to go to Mars, for example, you speed up, you move outward, adding energy to your orbit around the Sun. But if you want to go inward toward the Sun, you need to do something that feels counterintuitive. You need to slow down, not in the sense of moving slowly through space, but in the sense of reducing your sideways motion around the Sun. Remember, Earth is already moving at about 30 kilometers per second around the Sun. Anything launched from Earth inherits that motion. So if you were to point a spacecraft directly at the Sun and fire your engines, you wouldn't fall straight inward. You'd still be moving sideways, continuing to orbit. To actually move closer, you need to cancel out some of that sideways velocity, and that's extremely difficult. It requires a huge amount of energy, far more than most rockets can provide directly. So instead of trying to do it all at once, the Parker Solar Probe uses a different strategy. It borrows energy from another planet, specifically Venus. Over the course of its mission, the spacecraft performs multiple flybys of Venus, using its gravity to gradually reshape its orbit. Each pass changes the spacecraft's speed and direction slightly, lowering its closest approach to the Sun. Not a single dramatic maneuver, but a series of careful adjustments, step by step, orbit by orbit, each one bringing it closer. This approach takes time, years in fact, but it allows the spacecraft to reach distances that would otherwise be impossible with direct propulsion alone. Now, as the Parker Solar Probe moves inward, something remarkable happens. It doesn't just approach the Sun, it enters the Sun's outer atmosphere, known as the corona. This is where the idea of getting close starts to take on a new meaning. Because the corona isn't a solid boundary, it's an extended region of plasma stretching millions of kilometers into space. So when the spacecraft crosses into it, it's not landing or touching in the traditional sense. It's moving through a region where the Sun's influence is no longer distant, it's immediate. And this is where all the concepts we've been building come together. Radiation, energy balance, material limits, everything becomes more demanding. Now, you might expect that a spacecraft entering such an environment would simply overheat and fail, but the Parker Solar Probe is designed very carefully to avoid that outcome. At the front of the spacecraft is a heat shield. Not just any shield, but one specifically built to handle extreme conditions. It's made of a carbon composite material about 11.5 centimeters thick, with a white ceramic coating on the side facing the sun. That coating reflects a large portion of the incoming radiation. The underlying material absorbs some of what remains, but it's designed to withstand very high temperatures without losing its structural integrity. At its closest approach, the side of the shield facing the sun can reach temperatures of around 1,300 degrees Celsius. That's extremely hot. But here's the important part. The rest of the spacecraft, sitting in the shadow of that shield, remains much cooler. Around room temperature, in fact. This works because of something we discussed earlier. Radiation travels in straight lines. If you block it effectively from one direction, you can create a protected region behind that barrier. And in the vacuum of space, there's no air to carry heat around the edges, so the shadow remains stable. Now, maintaining that protection requires precision. The spacecraft must keep its heat shield pointed directly at the sun at all times. Even a small misalignment could expose sensitive components to direct radiation. So the Parker Solar Probe is equipped with systems that constantly adjust its orientation, ensuring that the shield stays between the sun and the rest of the spacecraft. This isn't optional, it's essential. Now, there's another interesting detail about the environment the spacecraft travels through. The corona, despite being extremely hot in terms of particle energy, is also very diffuse. That means the actual number of particles present is quite low. So even though individual particles can carry a lot of energy, there aren't enough of them to transfer heat in the way a dense gas would. This is another reason why the spacecraft doesn't instantly melt. It's not surrounded by a dense hot medium. It's exposed to intense radiation and energetic particles, but the overall environment still allows for controlled heat management. Now, as the Parker Solar Probe continues its mission, each orbit brings it closer, closer than any previous spacecraft, closer than Mercury. At its closest approach, it comes within about 6 million kilometers of the Sun's surface. That might still sound like a large distance, and it is. But compared to Earth's distance of 150 million kilometers, it's very close. Close enough that the sun fills a large portion of the sky. Close enough that the intensity of radiation is vastly greater than anything experienced near Earth. And yet the spacecraft survives. Not indefinitely, not without limits, but long enough to gather data, to measure the solar wind, to study the structure of the corona, to observe phenomena that were previously inaccessible, and this is where the significance of the mission becomes clear. It's not just about getting close, it's about understanding. By moving into this region, the Parker Solar Probe provides direct measurements of conditions that were once only inferred from a distance. It allows scientists to test theories, refine models, and gain a clearer picture of how the sun behaves. And in doing so, it also helps answer the question we've been building toward. How close can something actually get? Because the answer isn't just theoretical anymore, it's been demonstrated. Not all the way to the sun's core, not even to its visible surface, but deep enough into its outer layers to show what's possible. Now, there's something quietly reassuring about this. The idea that even in such an extreme environment, careful design and understanding can allow something to survive. Not by resisting the sun completely, but by adapting to it, working within its rules, managing its energy. And that idea carries forward, because as we continue moving closer in this journey, the conditions will become more demanding, the margins smaller, the balance harder to maintain, but the principles remain the same: energy in, energy out, protection, orientation, limits. Numbers have a way of sounding impressive without really feeling meaningful. You can say that something has travelled millions of kilometres, that it has reached record-breaking proximity, that it has gone closer than anything before it, and all of that is technically correct. But unless you pause for a moment and place those numbers into context, they remain distant in a different way, abstract. So instead of starting with the record itself, it helps to take a slower approach and ask a more grounded question. What does close actually mean when it comes to the sun? Because as we've already seen, The Sun isn't a solid object with a clear surface you can measure distance from in the usual way. There's no line you can draw and say, this is where it begins. Instead, there are layers. Regions where conditions change gradually, each one blending into the next. So when we talk about getting close, we're really talking about how far into those outer regions something can go while still functioning. And that brings us back to the Parker Solar Probe. This spacecraft holds the current record for the closest approach to the Sun. At its nearest, it travels to within about 6 million kilometers of what we would loosely call the Sun's surface, the photosphere. Now 6 million kilometers is still a very large distance by everyday standards. If you compare it to the size of Earth, which is about 12,700 kilometers in diameter, that gap is enormous. But in the context of the Sun, it's very close, because the Sun itself is about 1.4 million kilometers wide. So at its closest approach, the spacecraft is only a few solar radii away from the visible edge, and more importantly, it's deep within the region where the Sun's atmosphere extends outward. This is where the idea of records becomes more interesting. Because the Parker Solar Probe isn't just getting close in terms of distance, it's entering a region where the Sun's influence is direct and continuous, a place where the solar wind is still forming, where magnetic fields are active, and where the environment is shaped almost entirely by the Sun itself. Now, before this mission, other spacecraft had approached the Sun, but none had gone this close. Each one added a piece to the puzzle. Each one extended our reach a little further inward, but there was always a limit, a point beyond which conditions became too difficult to manage with existing technology. And for a long time, that limit remained well outside the region the Parker Solar Probe now explores. So what changed? Not the Sun, not the fundamental physics. What changed was our ability to design systems that could operate within those conditions. Better materials, better understanding of radiation, better control of spacecraft orientation, and heat management. All of these improvements made it possible to push that boundary inward. Now, there's something else that makes this record particularly interesting. It's not a single moment. The Parker Solar Probe doesn't just make one close pass and stop. It follows a series of orbits, each one bringing it closer than the last. This gradual approach is important because it allows engineers and scientists to observe how the spacecraft behaves under increasing levels of intensity, to monitor temperatures, to adjust expectations, to refine models. So the record isn't just about how close it gets, it's about how it gets there, step by step, orbit by orbit, each pass building on the last. Now, if you imagine being on board, or even just observing from a distance, the difference between each approach would be noticeable. The Sun would appear larger, brighter, more dominant in the field of view. The radiation levels would increase, the energy arriving at the spacecraft would rise, and yet the systems would continue to function. Because they were designed with these conditions in mind. Now, here's something worth pausing on. Even at its closest approach, the Parker Solar Probe is not touching the Sun in the way you might expect. It's not reaching a surface. It's not entering a region where everything suddenly changes from space to something else. Instead, it's moving through a gradient, a region where the density of particles increases, where magnetic fields become more complex, and where the Sun's influence becomes more immediate. This is why defining a record in terms of distance alone can be a bit misleading, because the experience of being at 6 million kilometers is very different from being at, say, 10 million kilometers, even though both distances are small compared to the overall scale of the solar system. The difference lies in the environment, in how much energy is present, in how strongly the Sun's processes are felt. Now, consider how this compares to Mercury. Mercury orbits at an average distance of about 58 million kilometers from the Sun. So the Parker Solar Probe, at its closest, is about 10 times closer than Mercury. That's a significant difference, not just in distance, but in intensity. Because as we discussed earlier, reducing distance increases energy rapidly. So being 10 times closer doesn't mean 10 times more intense, it means much more than that. And this is where the record becomes more meaningful, because it represents entry into a region that is fundamentally different from anything experienced by a planet. Now, there's another record associated with this spacecraft that often gets mentioned: speed. As it approaches the Sun, the Parker Solar Probe reaches speeds of over 190 kilometers per second. That's faster than any human-made object has ever travelled. And that speed is not just a side effect. It's part of how the spacecraft navigates the Sun's gravitational field. As it falls inward, it accelerates, gravity pulling it faster and faster as it approaches its closest point. Then, as it moves away again, it slows down. This repeated cycle of acceleration and deceleration is part of its orbit. And it's another reminder that getting close to the Sun isn't just about distance. It's about motion, about how objects move within the Sun's gravitational influence. Now, if you step back and look at the bigger picture, something becomes clear. We've already crossed a threshold that once seemed unreachable. We've sent something into the Sun's outer atmosphere. We've gathered data from regions that were previously only theoretical. We've demonstrated that it's possible to survive, at least for a time, under conditions far more intense than those near Earth. But at the same time, we haven't reached the end. There's still a gap, still a distance between the closest approach and the deeper layers of the Sun, and that gap represents the next set of challenges. Because while the Parker Solar Probe can survive at its current distance, moving closer would require even more advanced solutions, more effective shielding, better materials, more precise control. And eventually there comes a point where those solutions may no longer be enough. Now, it's also worth noting that how close we've gotten is not a fixed answer. It's a moving boundary. Each new mission has the potential to push it further, to refine what we consider possible, to extend our reach. But each step inward becomes harder, not just because of the increasing intensity, but because of the diminishing margin for error. At greater distances, small mistakes can be corrected. Closer in, the same mistakes can become critical. Now, there's something quietly interesting about this progression. It mirrors the way we've approached many challenges in science. Not by making a single leap, but by building gradually, testing limits, adjusting, trying again. And over time, what once seemed out of reach becomes part of what we can do. So when we ask how close we've already gotten, the answer is not just a number, it's a story, a record of how far we've pushed the boundary so far, and an indication of where that boundary might move next. Because the question isn't finished. Not yet. There's still more to understand about what happens as you move deeper into the Sun's environment. Not everything that protects you is something you can see clearly. That might sound a bit unusual at first, especially when we're talking about something as extreme as approaching the Sun, but it turns out to be quite accurate. Because the most important protection a spacecraft has isn't just a solid object sitting in front of it. It's a combination of design choices, positioning, and a very careful understanding of how energy behaves. So when we talk about a shield, it's helpful to think of it less as a wall and more as a system that creates conditions where survival becomes possible. Now there is a physical shield, of course. The Parker Solar Probe carries one at its front, and it's absolutely essential. But what makes it effective isn't just its thickness or its material. It's how it interacts with radiation, how it's positioned, and how everything behind it is arranged. Because simply placing a barrier between an object and the Sun wouldn't be enough on its own. The challenge isn't just blocking energy, it's managing what happens to that energy after it's blocked. Let's start with the most obvious part, the heat shield itself. At first glance, you might imagine something dense, heavy, maybe metallic, something that absorbs heat and keeps the rest of the spacecraft safe by sheer resistance. But that's not quite how it works. The shield is made primarily from carbon-based materials, designed not just to absorb heat, but to handle it without changing shape or structure. Carbon, in certain forms, can tolerate very high temperatures without melting in the traditional sense. And that's important because the temperatures involved are far beyond what most everyday materials could handle. But absorbing heat is only part of the story. because if the shield simply absorbed all the incoming energy without doing anything else, it would continue to heat up indefinitely, and eventually, even the most resilient material would fail. So the shield also needs to release energy. It does this by radiating heat away. The side facing the sun reflects a significant portion of incoming radiation, reducing how much energy is absorbed in the first place. The rest is handled by the material's ability to emit infrared radiation, allowing excess energy to leave the system. So the shield is constantly in a state of balance, energy arriving, energy leaving, and as long as those two processes remain in equilibrium, the shield can maintain a stable temperature. Now, here's where things become a bit more subtle. The shield doesn't protect the spacecraft by cooling everything down, it protects it by creating a shadow. And in space, that shadow is incredibly effective. On Earth, shadows are soft. Light scatters through the atmosphere, reflecting off surfaces, filling in the darker areas. In space, there's no such scattering. Light travels in straight lines, so if you block it in one direction, you create a region behind the shield where direct radiation simply doesn't reach. That region is where the rest of the spacecraft sits. Not in darkness exactly, because some energy is still present, but in a significantly reduced environment compared to the side facing the sun. And that difference can be dramatic. The front of the shield may be experiencing temperatures of over 1,000 degrees Celsius, while just behind it, conditions remain close to what we would consider normal operating temperatures for electronics. That contrast is what makes the system work, but it only works if the orientation is maintained. The shield has to stay between the sun and the spacecraft at all times. Even a small deviation could allow direct radiation to reach components that aren't designed to handle it, so the spacecraft is constantly adjusting its position. Tiny corrections made continuously, ensuring that the shield remains aligned. This is part of what makes the protection invisible. It's not just the presence of the shield, it's the ongoing process of keeping it in the right place. Now, let's think about what happens to the energy that does get through. Because no shield is perfect. Some radiation is absorbed, some heat is conducted through materials, and all of that needs to be managed. Inside the spacecraft, systems are designed to handle this. Components are arranged so that heat can be distributed and released efficiently. Radiators are positioned to emit excess energy into space. Insulation prevents heat from moving too quickly into sensitive areas. It's a layered approach. Not a single line of defense, but multiple systems working together. And this layered design is what allows survival over extended periods. Now, there's another aspect that isn't immediately obvious. Distance from the shield. The spacecraft isn't pressed right up against it. There's a separation, and that separation matters. Because even though there's no air in space, heat can still move through materials. By placing some distance between the shield and critical components, engineers reduce the rate at which heat can transfer inward. It gives the system more time to manage the energy, more time to radiate it away before it reaches something sensitive. So again, the protection isn't just about blocking, it's about controlling flow, slowing it down, redirecting it, allowing time for balance to be maintained. Now, consider how all of this comes together. The shield reflects and absorbs radiation. The spacecraft stays in its shadow. Internal systems distribute and release any remaining heat, and orientation keeps everything aligned. Each part alone wouldn't be enough, but together they create an environment where survival becomes possible, even in conditions that seem extreme. Now, there's an interesting point here. The shield itself gets very hot, extremely hot, and yet that doesn't mean the spacecraft as a whole is experiencing the same conditions. Because temperature in this context is local. It depends on where you are and what you're exposed to. The front of the shield can be at one temperature, the back at another, the interior at something entirely different, and that separation is what allows different parts of the system to operate within their limits. Now, as the spacecraft moves closer to the sun, the demands on this system increase. The incoming energy rises, the equilibrium temperature of the shield increases, the margin for error becomes smaller. But as long as the balance is maintained, the system continues to function, and that's the key idea. Survival near the sun isn't about eliminating heat. It's about managing energy, understanding how it moves, how it interacts with materials, and how to keep it within controllable limits. Now, there's one more layer to this. Because the sun doesn't emit energy in a perfectly steady way. There are variations, solar flares, changes in the solar wind, fluctuations in radiation levels, and the spacecraft has to handle those as well, not just a constant environment, but a dynamic one. So the design includes margins, allowances for variation, the ability to handle spikes in energy without immediate failure, and this adds another dimension to the concept of a shield. It's not just a static barrier, it's part of a system designed to operate under changing conditions. Now, as we continue moving inward in this journey, something becomes clear. The closer you get, the more demanding these systems become. The more precise the control needs to be, the more carefully energy must be managed. And eventually, there comes a point where even the best designed system begins to approach its limits. Not because the design is flawed, but because the environment becomes too intense, the incoming energy too great, the balance too difficult to maintain. Long before anything actually fails, matter begins to behave differently. That's an important detail because when people imagine getting close to the sun, they often picture a sudden moment, a clear boundary where things go from stable to destroyed in an instant. But in reality, the transition is gradual. Materials don't simply cross a line and disappear, they change step by step as the conditions around them become more demanding. So instead of asking when something melts or breaks, it's more useful to ask what happens along the way, because those changes start earlier than you might expect. At a distance like Earth's orbit, most materials behave exactly as you'd expect them to. Metals stay solid, plastics keep their shape, and structures remain stable under normal conditions. The sun's influence is present, but it's moderated, filtered through atmosphere, reduced by distance, and balanced by the environment around you. As you move closer, that balance begins to shift. Not suddenly, but noticeably. The first changes are subtle. Temperatures rise, but not enough to cause immediate damage. Instead, materials expand slightly. Metal components grow just a bit larger. Connections that were once tight begin to loosen if they're not designed to accommodate that expansion. This might sound minor, but in precise systems, even small changes can matter. A component that expands unevenly can create stress. A structure that heats at different rates across its surface can begin to warp. And this is one of the earliest ways the sun starts to influence matter more directly. Through differences in temperature across small distances. Now, continue moving inward. The intensity of radiation increases, and with it, the rate at which energy is absorbed. At this stage, materials begin to reach higher equilibrium temperatures. Metals that were comfortably solid before are now approaching the limits of their stability. Some may begin to soften, not melt outright, but lose rigidity. Their mechanical properties change, strength decreases, flexibility increases, and this can affect how structures hold together. Now, it's important to remember something we've touched on before. Melting isn't the only form of failure. In fact, it's often not the first. Before a material melts, it may weaken. Before it weakens, it may expand unevenly. Before that, it may experience internal stress. So as conditions become more intense, matter doesn't simply transition from fine to not fine. It moves through a series of states, each one slightly less stable than the last. Now let's take this a step further. As you move closer still, the role of radiation becomes more significant. Not just in heating materials, but in interacting with them on a deeper level. High energy radiation, particularly in the ultraviolet range, can begin to break chemical bonds. This is especially relevant for materials like plastics, coatings, and certain composites. At Earth's distance, these effects are relatively slow. They occur over long periods, but closer to the sun, the rate increases. Materials degrade more quickly, surfaces become brittle, protective layers begin to fail, and once those layers are gone, the underlying material is exposed to even more intense conditions. So degradation becomes a chain reaction. One layer fails, exposing the next. That layer fails, exposing another. And over time, the structure as a whole becomes compromised. Now consider what happens to something like a metal surface. At higher temperatures, oxidation can occur if there's an atmosphere, but in space that process is different. Without oxygen, you don't get the same kind of rusting you would on Earth. Instead, the primary effects come from heating and radiation. Metals can begin to evaporate, not in a dramatic boiling sense at first, but slowly, atoms gaining enough energy to leave the surface. This process is called sublimation, when it occurs directly from solid to gas. And while it's slow at lower temperatures, it becomes more significant as temperatures rise. So over time, even solid materials can lose mass, gradually, steadily, as atoms escape into space. Now, let's move even closer. At this stage, the temperatures are high enough that melting becomes unavoidable for many materials. Metals that once held their shape begin to liquefy. Structures lose their integrity. Components that relied on rigidity can no longer function. But even here, the process isn't necessarily immediate. It depends on the material, on how quickly it absorbs energy, on how effectively it can radiate heat away. Some materials will fail sooner, others will last longer, but the direction is clear. As the balance shifts further toward incoming energy, stability becomes harder to maintain. Now there's another transition beyond melting. At even higher temperatures, materials don't just melt, they vaporize. The liquid phase becomes unstable, and atoms gain enough energy to leave entirely forming a gas. And at that point, the concept of a solid object begins to break down. Because the material that once made up that object is no longer held together, it's dispersing, expanding, becoming part of the surrounding environment. Now here's where things start to become more interesting. Because near the Sun, the environment itself is already made of plasma, a state of matter where atoms are so energized that electrons are no longer bound to nuclei. Instead, you have a mixture of charged particles, ions and electrons moving independently, and as materials approach these conditions, they begin to transition toward that state, not instantly but progressively. First, molecules break apart, then atoms, then electrons are stripped away, and what was once a solid object becomes something closer to a cloud of charged particles. Now this might sound like a dramatic endpoint, and in many ways it is, but again it's not a single moment, it's a progression, and that progression depends on both the material and the environment. Different materials reach these stages at different distances. Some resist longer, some transition more quickly, but all of them follow the same general path: solid, then weakened, then melted, then vaporized, then ionized. Now consider how this applies to the question of how close you can get, because the answer isn't just about distance, it's about when these transitions occur. At what point does a material begin to fail in a way that prevents it from functioning? At what point does it lose its structure? At what point does it stop being what it was? And those points are not the same for everything. A material designed for high temperatures can survive closer than one that isn't. A system designed to manage radiation can last longer than one that simply absorbs it. So the limit isn't fixed, it depends on what you're using. Now, there's one more subtle point worth considering. Even before materials reach these extreme states, their properties can change in ways that affect how they interact with radiation. For example, a surface that was reflective at lower temperatures may become less reflective as it heats up, which means it absorbs more energy, which increases its temperature further, and that creates a feedback loop. More absorption leads to higher temperatures, which leads to even more absorption, and that accelerates the process. So the closer you get, the more these feedback effects come into play, and the more important it becomes to manage not just the amount of energy, but how materials respond to it. Now, stepping back for a moment, something becomes clear. The sun doesn't destroy matter in a single dramatic way. It transforms it, gradually, systematically, through well-understood processes, each one driven by increasing energy, and each one defining a different boundary. So when we ask how close something can get, we're really asking how far it can go before those transformations reach a point where the original structure can no longer exist. And that point varies, but it always exists, because no material can resist increasing energy indefinitely. Eventually the balance tips, and the structure gives way. Try picturing an atmosphere that behaves in ways your intuition wouldn't expect. On Earth, the idea is simple. You move higher, and the air gets thinner and colder. Heat tends to stay closer to the surface because that's where most of the energy is absorbed and redistributed. It feels consistent, predictable, something you don't need to question. But the sun doesn't follow that pattern. As you move outward from what we see as its visible surface, the photosphere, you don't enter a region that becomes cooler and quieter. Instead, you step into something that becomes hotter, not slightly hotter, but dramatically so. And that shift is where things begin to feel less familiar. The outer atmosphere of the sun, known as the corona, stretches millions of kilometers into space. It's not a thin shell sitting just above the surface. It's an extended region, fading gradually into the surrounding space, blurring the line between star and environment. So when we talk about approaching the sun, we're not aiming for a clear boundary. We're moving into this halo. Now, here's where the unusual part comes in. The temperature of the photosphere, the layer you see when you look at the sun, is around 5,500 degrees Celsius. That's already extremely hot. But as you move outward into the corona, the temperature rises to over 1,000,000 degrees. That seems backwards. It suggests that moving away from the main source of energy leads to higher temperatures, which doesn't match everyday experience. So how can that be? The answer lies in how temperature is defined in this context. In everyday life, temperature often reflects how something feels, how much heat it can transfer to you. In the corona, temperature refers to the energy of individual particles. Those particles can be moving extremely fast, carrying a lot of energy, even if there aren't very many of them. And that's the key detail. The corona is incredibly diffuse. There are far fewer particles than in the photosphere. So even though each particle is very energetic, the overall density is low. That means the environment is hot in terms of particle energy, but not dense enough to transfer that heat in the way a solid or liquid would. So if you were somehow present in the corona, the experience wouldn't be like being submerged in a hot fluid. You wouldn't feel a surrounding pressure of heat in the way you might expect. Instead, you'd be exposed to high-energy particles and intense radiation, but with relatively little direct contact between particles. This distinction matters, because it explains how something like the Parker Solar Probe can move through the corona without instantly reaching those 1,000,000-degree temperatures itself. The particles are energetic but sparse. The spacecraft interacts with them, but not in a way that overwhelms it immediately. Now, the corona isn't uniform. It's structured by magnetic fields. The sun's magnetic field is complex and constantly changing, and it shapes the movement of plasma in the corona. You can see this in images of the sun taken during eclipses or with specialized instruments. The corona appears as a glowing halo, with streamers and loops extending outward. Those shapes are not random. They trace the paths of magnetic field lines, guiding the movement of charged particles. So as you move into this region, you're not entering a calm, uniform environment. You're entering something dynamic, plasma flowing along invisible paths, energy being transferred in ways that are not immediately obvious. Now, there's another layer to this. The corona is where the solar wind originates, that constant stream of charged particles flowing outward from the sun. At greater distances, we think of the solar wind as something that passes through space, but here, near its source, it's still forming, still being accelerated, still interacting with the sun's magnetic field, So the environment becomes more active, more complex, and this activity adds to the challenge of getting close. Because it's not just about managing radiation and heat, it's about dealing with a moving, changing system. Now consider how this affects matter. As we discussed earlier, materials respond to increasing energy in stages. They heat up, they degrade, they eventually melt or vaporize. But in the corona, there's an additional factor: charged particles, high-energy ions and electrons moving at significant speeds. These particles can interact with materials in ways that go beyond simple heating. They can erode surfaces, knock atoms loose, gradually wear down exposed areas. This process is slow at larger distances, but closer in it becomes more significant. So the challenge isn't just surviving temperature, it's surviving a combination of effects: radiation, particle interactions, magnetic influences, all acting together. Now, let's return to the idea of the sun having an atmosphere. On Earth, the atmosphere is something you move through gradually. You climb a mountain and the air becomes thinner. You go higher and eventually you reach space. There's a transition, but it's relatively well defined. With the sun, that transition is less clear. The corona doesn't end at a specific point. It fades, gradually blending into the solar wind, which then extends throughout the entire solar system. So in a sense, you're already inside the sun's atmosphere, even at Earth's distance. It's just extremely thin here, barely noticeable unless you're looking for it. But as you move closer, that presence becomes more pronounced. The density increases, the activity increases, and the environment becomes more distinctly solar. Now, there's something else that's worth noticing. The corona is visible under certain conditions. During a total solar eclipse, when the bright disk of the sun is blocked by the moon, the corona appears as a faint glowing halo around it. That halo is the outer atmosphere, the same region the Parker Solar Probe moves through. And seeing it like that gives a sense of scale. It extends far beyond the visible surface, far enough that approaching the sun means entering this extended region long before you reach anything resembling a boundary. Now, as you imagine moving through the corona, the idea of touching the sun becomes less straightforward, because you're already interacting with it, already within its influence, already moving through its outer layers. There's no single moment where you arrive, no clear point where you can say, this is it. Instead, it's a gradual immersion, conditions becoming more intense, more complex, more demanding. Now, consider how this fits into the question we started with. How close could you really get? The answer isn't just about reaching a certain distance, it's about how far into this environment you can go while maintaining control, while keeping systems stable, while managing the increasing energy and activity. And the corona represents a significant part of that journey, because it's the first region where the sun stops being something distant and becomes something you're moving through. Now, there's still a difference between being in the corona and reaching the deeper layers of the sun. The density increases as you move inward, the energy becomes more concentrated, the environment becomes more difficult to manage. But the corona is where the transition begins, where the sun's atmosphere becomes something you experience directly. And that makes it a natural point to pause and consider what contact really means. Because if you're already inside this extended atmosphere, already interacting with its particles and fields, then the idea of touching the sun isn't as simple as reaching a surface. It's about entering a process, a system that extends far beyond what you see from Earth. Imagine trying to define the exact moment when you enter something that doesn't have a clear edge. Not a wall, not a surface, not even a boundary you could draw with a line. Just a gradual change, a shift in conditions that becomes more noticeable the deeper you go. That's what it's like when we talk about touching the sun. Because unlike a planet, the sun doesn't give you a place to land. There's no solid ground waiting beneath the brightness. No moment where your feet would meet a surface and confirm that you've arrived. Instead, there's a transition, and that transition begins in the corona. Now, we've already talked about the corona as the sun's outer atmosphere, extending millions of kilometers into space. But what makes this region particularly important isn't just how far it reaches, it's how it behaves. Because the corona isn't just something you observe from a distance, it's something you can move through. And that changes the meaning of close. When the Parker Solar Probe made its historic passes near the Sun, it didn't just approach it visually. It entered this region, crossed into it, and in doing so, it provided a new way to think about what it means to get close. Now, here's the key idea. The corona is made of plasma, charged particles moving under the influence of the Sun's magnetic field, and as you move closer, the density of that plasma increases. Not dramatically at first, but steadily, so instead of crossing a sharp boundary, you pass through a gradient. At some point, the environment changes enough that you're no longer in what we would call interplanetary space. You're in the Sun's atmosphere. That point is sometimes referred to as the Alphen surface, a region where the behaviour of the solar wind changes. Outside this boundary, the solar wind flows freely outward, largely unaffected by the Sun's magnetic field. Inside it, the magnetic field dominates. The plasma is more tightly connected to the Sun, and movement becomes more structured, more influenced by magnetic forces. Crossing this boundary isn't something you would feel directly. There's no sudden jolt, no dramatic shift in temperature or pressure, but scientifically it's a meaningful transition, because it marks the point where the Sun's influence becomes more immediate, more direct. Now, think about what that means. At Earth's distance, the solar wind is something that passes by, a background flow of particles that interacts with our planet's magnetic field but doesn't define the entire environment. Inside the corona, that relationship changes. You're no longer in a region where the Sun's influence is something you observe. You're in a region where it defines the conditions. And this is why some scientists say that crossing into the corona is, in a sense, touching the Sun. Not touching a surface, but entering the system itself. Now, let's consider what happens to matter in this region. Earlier we talked about how materials respond to increasing energy, heating up, degrading, eventually reaching points where they can no longer maintain their structure. In the corona, those processes are still at work, but they're joined by something else: direct interaction with plasma, charged particles moving at high speeds. These particles can collide with surfaces transferring energy, knocking atoms loose, gradually eroding materials. This process is subtle at first, slow, but it becomes more significant the closer you get. So the environment isn't just hot, it's active, dynamic, and that activity adds another layer to the challenge of surviving here. Now here's something that might seem counterintuitive. Despite the high temperatures associated with the corona, being inside it doesn't feel like being inside a hot fluid. Because the density is still low, there aren't enough particles to transfer heat in the way a dense gas would. So the experience remains dominated by radiation and direct particle interactions, not by surrounding heat. This is why a spacecraft can pass through the corona without instantly reaching those extreme temperatures. The energy is present, but it's not delivered in a way that overwhelms everything at once. Instead, it builds, and as long as the spacecraft can manage that incoming energy, it can continue to operate. Now consider how this changes your perspective on touching the Sun. If you think of the Sun as a solid object, then touching it would mean reaching its surface. But if you think of it as a system, extending outward through the corona and beyond, then touching it becomes something else. It becomes entering that system, interacting with it directly, and that interaction begins well before you reach the visible surface. Now, there's another detail worth exploring. The corona isn't uniform, it's shaped by magnetic fields. These fields create structures, loops, arcs, streamers, regions where plasma is guided along specific paths. So as you move through the corona, you're not just moving through a uniform environment, you're moving through a structured one, where conditions can vary depending on where you are. Some regions may have higher densities, others stronger magnetic fields, some more active, others relatively calm. and this variability adds complexity, because it means that the environment isn't just defined by distance, it's also defined by location within the Sun's magnetic structure. Now, as you continue moving inward, the density increases further, the interactions become more frequent, the energy more concentrated, and the environment becomes harder to manage. But the transition remains gradual. There's no single moment where everything changes, just a steady progression. Now, let's pause for a moment and consider what this means for the question we've been following. How close could you really get? We've already moved beyond the idea of a simple distance. We've seen that getting close involves entering a region where the Sun's influence becomes direct, where radiation, particles, and magnetic fields all play a role, and the corona is the first major step in that process. It's where the journey shifts from approaching to entering, from observing to interacting. Now, beyond the corona, deeper layers of the Sun become more challenging. The density increases, the temperature rises, the environment becomes less forgiving. But even here, in this outer atmosphere, you can already see the limits beginning to take shape, not as a single boundary, but as a series of conditions, each one more demanding than the last, and each one defining how far something can go. Now, there's one more aspect to consider: time. Because surviving in the corona isn't just about withstanding the conditions at a single moment. It's about maintaining stability over time, managing energy continuously, handling variations, adapting to changes. And that's what makes missions like the Parker Solar Probe so significant. They don't just pass through once, they return, again and again, each pass lasting longer, each one providing more data, more understanding, and showing that, with the right design, it's possible to operate within this region, not indefinitely, not without limits, but long enough to learn. Now, as we continue this journey inward, the question becomes more focused. Not just how close you can get, but what happens as you move beyond this point. As the density increases, as the environment becomes more intense, as the balance between incoming and outgoing energy becomes harder to maintain. Because while the corona represents the beginning of direct contact, it's not the end. There are still deeper layers ahead, still regions where the conditions change further. The Sun doesn't offer a single answer. It offers a range, a spectrum of conditions, and the closer you move, the more that spectrum reveals where the limits truly are. Consider, for a moment, removing all the engineering. No heat shields, no reflective coatings, no carefully calculated trajectories, just a human body, placed somewhere along the path we've been slowly tracing inward. It's a simple idea, but it changes the question immediately. Because everything we've discussed so far, radiation, energy balance, material limits, has been framed in terms of objects designed to survive, systems built specifically to manage the Sun's influence. A human body is not that. It's adaptable in many ways, but only within a narrow range of conditions. Temperature, pressure, radiation levels, all of these need to stay within limits that are quite small compared to the environments we've been describing. So instead of asking how close could you get, the question becomes more specific. At what point do those conditions exceed what the body can handle? And how quickly does that happen? Now, the first thing to understand is that the journey itself is already a problem. Leaving Earth isn't something a human body can do unprotected. The moment you step into space without a suit, the lack of pressure, the absence of oxygen, and the exposure to vacuum create immediate and serious challenges. Within seconds, consciousness would be lost. Within minutes, survival would no longer be possible. So from the very beginning, protection is required. A spacesuit or a spacecraft. Something that maintains pressure, supplies oxygen, regulates temperature, and shields against radiation. And that protection becomes the baseline. Because without it, the journey doesn't even begin. Now, let's assume that protection exists, that you're inside a spacecraft, something designed to keep you alive while moving through space. At Earth's distance, this is manageable. Astronauts live and work in orbit. exposed to conditions very different from those on the surface, but still within a range that can be controlled. Radiation levels are higher than on Earth, but not immediately harmful over short periods. Temperature differences are managed by the spacecraft systems. Life continues. Now begin moving inward. At first, not much changes. The spacecraft still provides protection. The environment outside becomes more intense, but inside conditions remain stable. This is the key point. For a human, survival near the sun is not about the external environment alone. It's about whether that environment can be kept outside. As long as the spacecraft can maintain its protective role, the human inside experiences something closer to normal. But that protection has limits, and those limits are defined by the same factors we've been discussing: radiation, heat, material stability. Now, let's consider radiation first. At Earth's distance, the atmosphere and magnetic field provide significant protection. In space, that protection is reduced, but still manageable for limited durations. Closer to the sun, radiation levels increase, not just in intensity, but in the range of wavelengths present. Ultraviolet radiation becomes stronger. High-energy particles from the solar wind become more significant, and over time, this increased exposure becomes a problem. Radiation doesn't need to be immediately overwhelming to be harmful. It accumulates, damaging cells, increasing the risk of long-term effects. Now, for a short journey, this might not be the limiting factor, but as exposure increases, it becomes more difficult to shield completely. Materials can block some radiation, but not all, and the closer you get, the more challenging it becomes to keep those levels within safe limits. Now, let's turn to heat. Inside a spacecraft, temperature is controlled. Systems regulate the internal environment, keeping it within a range suitable for human life. But those systems rely on the ability to manage incoming energy, to reflect, absorb, and radiate heat away. As the spacecraft moves closer to the sun, the incoming energy increases, and at some point, the systems designed to manage that energy begin to approach their limits. If the spacecraft cannot radiate heat away as quickly as it absorbs it, the internal temperature begins to rise, slowly at first, then more noticeably, and eventually it can reach levels that are no longer safe for human occupants. So survival depends not just on the presence of protection, but on its effectiveness at a given distance. Now, consider the human body itself. Even in a controlled environment, it generates heat. Metabolism produces energy, and that energy needs to be dissipated. On Earth, this is handled through a combination of conduction, convection, and evaporation. In a spacecraft, these processes are managed through systems that remove heat from the body and release it into space. But if the external environment makes it harder for the spacecraft to release heat, that balance becomes more difficult to maintain, and again, the closer you get, the more challenging it becomes. Now, there's another factor: time. Survival isn't just about whether conditions are tolerable at a single moment. It's about how long those conditions can be maintained. A brief exposure to higher radiation levels might be acceptable. A longer exposure might not. A short increase in temperature might be manageable. A sustained increase might not. So the question of survival becomes a question of duration. How long can the protective systems maintain a stable environment under increasing external stress? Now let's move closer still, into the region near Mercury's orbit. At this distance, the intensity of sunlight is several times greater than at Earth. The spacecraft must handle significantly more incoming energy. Heat shields become essential. Orientation becomes critical. Even small deviations can have large consequences. Inside, the human remains protected, as long as the systems hold. But the margin for error is smaller. The environment outside is less forgiving. Now, move closer again, into the region explored by the Parker Solar Probe. At this distance, the intensity of radiation is far beyond what a human could survive without substantial protection. Even with protection, the challenge becomes maintaining that protection. The heat shield must function perfectly. The spacecraft must remain oriented correctly. Systems must continue to manage energy without failure. And even then, the environment inside is dependent on those systems. If something goes wrong, the consequences are immediate. Now here's an important point. The human body itself is not directly experiencing the sun's environment. It's experiencing the environment created by the spacecraft. So the question of survival is really a question of engineering. How close can we maintain a human-compatible environment while moving through increasingly intense conditions? And the answer is not fixed. It depends on technology, on materials, on design. But it also depends on limits, because at some point the energy becomes too great. The systems required to manage it become too complex or too heavy. The margin for error becomes too small, and beyond that point, maintaining a stable environment becomes impractical. Now there's another aspect to consider: psychological factors. Even if the physical environment can be maintained, the experience of being so close to the sun, knowing the conditions outside, relying entirely on systems for survival, introduces its own challenges. But those are secondary to the physical constraints. Now, stepping back, something becomes clear. A human cannot survive the journey to the sun without protection. That part is straightforward. With protection, survival becomes possible up to a certain point. A point defined by how well that protection can manage increasing energy and radiation. And that point, at least with current technology, lies somewhere in the region we've already explored with spacecraft. Not at the surface, not deep within the sun, but within its outer regions, where the environment is intense but still manageable with the right design. A small step inward doesn't mean a small change in conditions. That's the part that tends to catch people off guard. When you picture moving closer to something, especially something visible like the sun, it's easy to imagine a steady progression, a gradual increase. You move a little closer, it gets a little brighter, a little warmer, and the pattern continues in a predictable way. But that's not how this works, because the sun isn't just an object sitting in space. It's a source of energy spreading outward in all directions, and the way that energy spreads creates a situation where distance can be misleading. Now, we've already touched on this idea before, but here it becomes central. The intensity of sunlight doesn't increase in a straight, simple way as you move closer. It follows a pattern where reducing distance leads to a much larger increase in energy than intuition suggests. To make that clearer, imagine this. If you were to move halfway closer to the sun, not all the way, just cutting the distance in half, the energy you receive wouldn't double. It would increase by a factor of 4, move closer again, and it increases again by that same factor. So each step inward amplifies the effect more than the last, and that's where the illusion comes in. Because visually, the sun doesn't seem to change that dramatically at first. From Earth, it appears as a disk in the sky. As you move closer, that disk grows, but slowly at large distances. It doesn't suddenly fill your entire view. It expands gradually, and that gradual visual change can give the impression that the environment is changing just as gently. But the energy tells a different story. The brightness increases, the radiation intensifies, the amount of energy arriving at any surface rises quickly, and that rise becomes more noticeable the closer you get. Now, consider Mercury again. From Mercury's orbit, the sun looks larger than it does from Earth, but not overwhelmingly so. It's bigger, brighter, more intense, but still recognizable as the same object. And yet, the energy at that distance is several times greater, already enough to create extreme conditions on the planet's surface. So even here, the visual change and the physical change are not aligned. The sun looks somewhat closer, but it behaves much closer. Now, let's take another step inward, closer than Mercury, into the region explored by the Parker Solar Probe. At this distance, the sun becomes more dominant in the sky. It occupies a larger portion of your field of view. The brightness is more intense. But still, it doesn't feel like you're right next to it, in the way you might imagine standing next to a large object. There's still space between you and it. still a sense of separation, and yet the energy is now vastly greater. The radiation levels are far beyond what you experience near Earth. The intensity is no longer something you can ignore or manage casually. It requires deliberate design, careful orientation, and constant control. So again, the illusion persists. Visually, you're closer. But physically, the change is much more dramatic than the view suggests. Now, here's where things become even more interesting. Because this disconnect between distance and energy isn't just a curiosity. It defines the limits of how close you can get. If you were to judge proximity based on how the sun looks, you might assume that you could move quite close before conditions become extreme. But if you judge it based on energy, the limits appear much sooner. Because energy doesn't wait for you to feel close. It increases according to its own rules, and those rules are not tied to perception. Now think about what this means for survival. Earlier we talked about how spacecraft manage energy, reflecting radiation, radiating heat away, maintaining balance. Those systems are designed based on energy, not appearance, because what matters is not how close something looks, but how much energy it's receiving, and that's what determines whether it can continue to function. Now, let's bring this back to the idea of a journey. If you were moving toward the sun, the first part of that journey might feel uneventful. The sun grows slightly larger, the brightness increases gradually. Nothing dramatic happens right away, but at the same time the energy is increasing, and at some point that increase crosses a threshold, not a visual threshold, a physical one, where materials begin to behave differently, where systems need to work harder to maintain balance, where protection becomes essential, and beyond that point, each additional step inward has a greater impact than the last. Now, there's another layer to this, because distance itself becomes less useful as a measure the closer you get. At large distances, changes in position don't affect energy very much. Moving 1,000,000 kilometers closer when you're far away doesn't change conditions dramatically, but when you're already close, that same change can have a much larger effect. So the scale compresses, not visually, but physically. Each unit of distance matters more. Each step inward carries more consequence. Now, consider how this affects the idea of getting as close as possible. If you think of it in terms of distance, you might imagine a final point, a closest approach, a single number that defines the limit. But in terms of energy, the limit isn't a single point. It's a region, a range where conditions become increasingly difficult to manage. And within that range, the difference between one position and another can be significant. Now, there's also something else worth noticing. The sun itself doesn't change as you approach. It continues emitting energy at the same rate. What changes is how that energy is distributed. Closer in, it's concentrated. Farther out, it's spread. So the environment you experience is not about the sun becoming more active. It's about you moving into a region where its energy is less diluted, and that distinction helps clarify something. The challenge of getting close isn't about the sun becoming more intense. It's about entering regions where its intensity is already high. Now, let's pause for a moment and connect this to everything we've discussed so far. We've seen how radiation carries energy, how materials respond to increasing exposure, how spacecraft manage that energy, how the corona extends outward, creating a gradual transition. And now we see how distance and energy are not the same. All of these pieces fit together, because they describe the same underlying process. Moving closer to the sun is not just a change in position, it's a change in conditions, conditions defined by energy. Trying to fall straight into the sun sounds simple. You let go, you drop inward, and gravity does the rest. It feels like the most natural motion you can imagine, especially when you think about how objects fall toward Earth. You release something, and it moves directly downward, pulled by gravity in a clear and predictable way. But once you step outside that everyday experience, the situation changes. Because in space, nothing starts from rest. Everything is already moving. Right now, as you sit wherever you are, you're not stationary in the larger sense. Earth is carrying you along at about 30 kilometers per second as it orbits the sun. That motion is constant, smooth, and almost impossible to notice without thinking about it. And that sideways motion is the reason you don't fall into the sun already. Gravity is pulling you inward, just as it pulls everything else, but your forward motion is balanced in such a way that you keep missing the sun. You fall toward it, but you also move sideways fast enough that you stay in orbit. It's a bit like throwing something forward while gravity pulls it down. If you throw it fast enough, it curves toward the ground but never quite reaches it, because the ground curves away beneath it. That's what orbit is. Continuous falling combined with continuous sideways motion. Now, here's where things become less intuitive. If you want to move closer to the sun, your first instinct might be to speed up. After all, going faster seems like the way to get somewhere more quickly. But in this case, speeding up in the direction you're already moving doesn't bring you closer. It pushes you outward. Because increasing your orbital speed raises your orbit, moving you farther from the sun rather than closer to it. So to move inward, you have to do the opposite. You have to slow down. Not in the sense of stopping completely, but in the sense of reducing your sideways velocity. That's what allows gravity to pull you into a lower orbit. And that's where the challenge begins. Because slowing down in space is not as simple as it sounds. There's no air resistance to help you, no friction to gradually reduce your speed. Everything continues moving unless you actively change it. So to reduce your orbital velocity, you need to use propulsion. You need to fire engines in the opposite direction of your motion, carefully and precisely. And the amount of energy required to do that is significant. Now, consider what this means in practical terms. Launching something from Earth already requires a great deal of energy. Reaching orbit is only the first step. Escaping Earth's gravity takes more, but even after you've done that, you're still moving around the sun at high speed. And to move inward, you need to cancel out a large portion of that speed. That's why getting closer to the sun can actually be harder than leaving the solar system entirely. To escape outward, you add energy. To fall inward, you remove it. And removing that much energy is not easy. Now this is where missions like the Parker Solar Probe take a different approach. Instead of trying to slow down all at once, which would require enormous amounts of fuel, they use gravity assists. Specifically, flybys of Venus. Each time the spacecraft passes near Venus, it exchanges energy with the planet's gravitational field. The result is a change in its orbit, a reduction in its sideways velocity relative to the Sun, and with each pass the orbit becomes slightly smaller. The spacecraft moves closer, not in a straight line but in a series of gradually tightening paths. This process takes time, years in fact, but it allows the spacecraft to reach distances that would otherwise be unreachable with direct propulsion alone. Now, let's think about what this looks like from a broader perspective. Instead of a direct fall, the path toward the Sun is more like a spiral, each orbit bringing you a little closer, each pass reducing your distance, and as you move inward, your speed changes as well. This is another point that can feel counterintuitive. Even though you need to slow down to get closer, once you begin falling inward, gravity accelerates you. So near the Sun, objects can move extremely fast. Faster than anywhere else in the solar system. The Parker Solar Probe, for example, reaches speeds of over 190 km per second at its closest approach. That's not because it's constantly accelerating under its own power, it's because it's falling deeper into the Sun's gravitational well. And that speed introduces another layer to the problem, because moving fast through an environment changes how you interact with it. Particles in the solar wind, for example, collide with the spacecraft more frequently and with greater energy. Radiation exposure increases not just because of proximity, but also because of motion. So getting closer isn't just about surviving higher energy levels, it's about doing so while moving at incredible speeds. Now let's return to the idea of a human making this journey. Even if you had a spacecraft capable of managing the heat and radiation, you would still need to follow this same process. You couldn't simply point yourself at the Sun and go. You would need to adjust your orbit, reduce your sideways velocity, carefully control your trajectory, and that would take time, Multiple maneuvers, possibly years of gradual adjustments, so the journey itself becomes part of the challenge, not just surviving the destination, but reaching it in the first place. Now there's another subtle point here. Because gravity doesn't just pull you inward, it also shapes the path you take. Depending on your speed and direction, you might end up in a stable orbit, or a highly elliptical one, or a trajectory that brings you very close and then sends you back out again. So getting close to the sun isn't a single action. It's a continuous process of adjustment, fine-tuning your motion to achieve the desired path. And that path determines how close you can get. Now, stepping back, something becomes clear. The difficulty of approaching the sun is not just about the environment, it's also about the journey. The need to reduce speed, the need to manage motion, the need to work within the constraints of orbital mechanics. All of these factors combine to make the process more complex than it first appears, so when we ask how close something can get, we're not just asking about survival at a given distance, we're asking about whether it can reach that distance at all. Because if you can't adjust your motion properly, you never get there. Even once you've managed to reduce your sideways motion, even once you've begun to fall inward, there's another challenge waiting. One that becomes more significant the closer you get. Not just how to move toward the sun, but how to control that movement as the forces involved become stronger. Most journeys feel like they're limited by how fast you can go. You want to reach something sooner, so you add speed. You accelerate, you push harder, you try to cover more distance in less time. That way of thinking works almost everywhere in everyday life, and even for many missions in space. But moving toward the sun reverses that logic in a way that feels almost uncomfortable. Because here, the problem isn't speed, it's too much of it. Right now, without doing anything at all, you're already moving incredibly fast around the sun. Earth carries everything on it, including you, at roughly 30 kilometers per second. That sideways motion is what keeps us in orbit, constantly falling toward the sun but never reaching it. So if you were to launch a spacecraft from Earth, it wouldn't start from rest. It would inherit that same motion. And that creates the core challenge. Because if you want to get closer to the sun, you need to reduce that sideways speed. Not increase it. Reduce it. Now, this might seem straightforward at first. You just slow down. But in space, slowing down is not passive. There's no air resistance to help you. No friction to gradually bring your speed down. Everything keeps moving unless you actively change it. So to reduce your speed, you need to use propulsion. You need to fire engines in the opposite direction of your motion, effectively pushing against the path you're already on. And that requires energy, a lot of it. Now here's where things become more interesting. The amount of energy required to reduce your orbital speed is enormous. In fact, it can be more demanding than the energy needed to leave the solar system entirely. That sounds counterintuitive, but it makes sense when you think about it. To escape the solar system, you add energy. You speed up until you're no longer bound by the sun's gravity. To fall inward, you have to do the opposite. You have to cancel out a significant portion of the energy you already have, and that's difficult, because you're starting from a very high baseline. Now imagine trying to come to a stop while already moving at tens of kilometers per second. There's no natural force helping you do that. You have to actively remove that motion, and every bit of speed you remove requires fuel. Now spacecraft carry limited fuel. They can't simply fire their engines continuously until they slow down enough. That would require more fuel than is practical to carry. So instead, missions that aim to get close to the sun use a different strategy. They take advantage of gravity, specifically the gravity of planets. The Parker Solar Probe, for example, uses repeated flybys of Venus. Each time it passes near Venus, it exchanges energy with the planet's gravitational field. This interaction changes the spacecraft's velocity relative to the sun. Not dramatically in a single pass, but enough to lower its orbit slightly. And by repeating this process multiple times, the spacecraft gradually reduces its sideways motion, step by step, orbit by orbit, each pass bringing it closer to the sun. Now, this approach has an important consequence. It takes time, years. The spacecraft doesn't simply head straight inward. It follows a carefully planned path, looping around the Sun, crossing Venus's orbit again and again, each time adjusting its trajectory. So getting close to the Sun is not a direct journey. It's a gradual one. Now there's another layer to this. Even as you reduce your sideways speed and begin to fall inward, gravity starts to accelerate you. The closer you get to the Sun, the stronger its gravitational pull becomes, and that pull increases your speed. So you're in a situation where you need to slow down to get closer, but once you do, you start speeding up again. This creates a kind of balance. You reduce your orbital energy to move inward, but gravity converts that change into increased speed along your path, and that's why spacecraft like the Parker Solar Probe reach such high speeds near the Sun. At its closest approach, it travels at over 190 kilometers per second. That's faster than any human-made object has ever moved. And it's not because it's continuously accelerating under its own power, it's because it's falling deeper into the Sun's gravitational field. Now this introduces another challenge, because moving at such high speeds affects how you interact with the environment. Particles in the solar wind collide with the spacecraft more frequently and with greater energy. Radiation exposure becomes more intense, not just because of proximity, but because of motion. So the faster you move, the more demanding the environment becomes. Now, consider what this means for a human journey. Even if you had a spacecraft capable of handling the heat and radiation, you would still need to manage this speed problem. You couldn't simply aim for the Sun and go. You would need to carefully reduce your sideways velocity, plan your trajectory, use gravity assists or other methods to adjust your motion, and that process would take time, it would require precision, and it would involve multiple steps. Now, there's another subtle point here, because slowing down doesn't just affect how close you can get, it also affects how long you stay there. If you approach the Sun on a highly elliptical orbit, you might pass very close at one point, then move away again. A brief encounter. But if you want to remain close for longer, you need to reduce your speed even further to settle into a tighter orbit, and that requires even more energy, so the closer you want to stay, the harder it becomes. Now stepping back, something becomes clear. The difficulty of getting close to the Sun isn't just about surviving the environment, it's about reaching that environment in the first place. The need to remove energy, the need to control motion, the need to balance gravitational forces and velocity. All of these factors combine to make the journey more complex than it first appears. So when we talk about how close something can get, we're not just talking about materials or heat shields. We're talking about trajectories, energy budgets, orbital mechanics. Because if you can't solve the speed problem, you never reach the point where the other challenges matter. The next question builds naturally from this. Because once you've managed to get close, once you've navigated the complexities of motion and arrived in a region where the Sun's influence is intense, the question becomes more immediate. Not just how you got there, but what you would actually experience, what it would feel like, what changes as the environment shifts from something distant to something surrounding. Imagine the journey not as a diagram or a set of numbers, but as something you're experiencing moment by moment. Not standing on Earth looking up, not reading about spacecraft, but being carried along, enclosed in something that keeps you alive while everything outside becomes less and less familiar. Because the question of what you would actually feel isn't answered by distance alone. It's answered by how your body, your senses, and your environment respond as conditions change. Now, the first thing to understand is that you wouldn't feel most of what's happening directly. Not at first. Leaving Earth already removes many of the sensations you're used to. No air movement, no natural temperature shifts across your skin, no pressure changes you can sense easily. Inside a spacecraft, everything is controlled, the air is stable, the temperature is steady, and your body is largely insulated from what's happening outside. So in the early part of the journey, even as you begin moving inward, Nothing dramatic happens from your perspective. The sun grows slightly larger, the light through any viewing window becomes brighter, but inside it still feels like a room, quiet, stable, familiar, and that's important, because it shows how much of your experience depends on the environment around you, not just what's happening outside. Now, as the spacecraft continues inward, the first noticeable change would likely be visual. The sun would begin to occupy more space in your field of view. At Earth's distance, it's a small disk. From Mercury's orbit, it appears larger, more dominant. Closer still, it begins to feel less like a distant object and more like a presence. Not something you can ignore. Something that draws attention even when you're not looking directly at it. And the brightness becomes more intense. Not just brighter in a comfortable way, but sharper. More difficult to look at, even with protection. Now, inside the spacecraft, the windows would likely be filtered, designed to reduce that brightness to safe levels, so what you see would be controlled. But even then, the change would be noticeable. The contrast between light and shadow would increase. The sun would feel less like part of the background and more like the center of everything. Now, in terms of physical sensation, things remain relatively calm as long as the spacecraft is doing its job. Temperature stays stable, air pressure remains constant. Your body doesn't suddenly feel hotter just because the sun is closer, and that's a key point. You don't directly feel radiation in the way you feel air temperature. You feel its effects. So as long as those effects are managed, your immediate experience doesn't change dramatically. But there are subtle shifts. The spacecraft systems will be working harder, managing more incoming energy, radiating more heat away, and while you wouldn't feel that directly, you might notice it indirectly. The hum of systems, the awareness that everything depends on them. Now let's move closer, into the region near Mercury. At this distance, the environment outside becomes much more intense. If you were to step outside, even briefly without protection, the experience would change quickly. The side of your body facing the sun would begin to absorb energy at a much higher rate. Your skin would heat rapidly. Not because the surrounding space is hot, but because the radiation is intense. There's no air to carry heat away, no breeze to cool you, just direct exposure. The sensation wouldn't be like standing in hot air. It would be more immediate, more localized, the exposed side heating quickly, while the shaded side remains much cooler. That contrast would be striking. But of course, you wouldn't survive long enough for that to become a prolonged experience, which is why the spacecraft remains essential. Now, moving closer still, into the region explored by the Parker Solar Probe, the outside environment becomes even more extreme. The intensity of radiation increases significantly. The sun fills a larger portion of the sky. The brightness is overwhelming. But inside, if everything is functioning correctly, the experience remains controlled. And that's where something interesting happens. There's a disconnect between what you know is happening outside and what you actually feel. You're aware that the environment is intense, that the spacecraft is protecting you from conditions that would be immediately harmful, but your body doesn't register those conditions directly. Instead, you experience a stable, controlled environment, and that creates a kind of contrast between knowledge and sensation. Now there are a few things you might feel, not from the sun itself, but from the journey. Acceleration, for example. During maneuvers, you might feel forces as the spacecraft adjusts its trajectory. But for much of the journey, motion in space is smooth. Without friction, without resistance, movement doesn't produce the same sensations as it does on Earth. So even as you're traveling at incredible speeds, you might not feel that speed directly. Another factor is orientation. The spacecraft needs to keep its heat shield pointed toward the sun. That means your view is constrained. The sun is always in a specific direction relative to the spacecraft, and that consistency might shape your perception, a constant reference point. Now, as you move deeper into the sun's outer atmosphere, the corona, the environment outside becomes more complex. Charged particles, magnetic fields, radiation, all interacting in ways that are difficult to visualize. But again, inside, the experience remains controlled, as long as the systems hold. And that's the key condition, because everything you feel depends on those systems. If they function correctly, your experience remains stable. If they begin to struggle, changes would start to appear. Temperature might begin to rise, not instantly but gradually, the systems working harder to maintain balance. If they can't keep up, the internal environment would begin to shift, and that's when your body would start to notice heat building, conditions becoming less comfortable. But ideally, those situations are avoided through design. Now, there's another aspect to consider: psychological perception. Knowing how close you are to the sun, seeing it dominate your view, understanding the conditions outside, all of that shapes how you experience the journey. Even if your body feels fine, your awareness might change. The sun no longer feels distant. It feels immediate, present. And that presence can be difficult to ignore. Now, stepping back, something becomes clear. The experience of travelling toward the sun is not defined by dramatic physical sensations. Not at first. It's defined by contrast. Between what's happening outside and what you feel inside. Between intensity and control. Between environment and protection. And that contrast remains as long as the protective systems continue to function. There comes a point where the gradual changes stop feeling gradual. Up to now, everything has followed a pattern that feels manageable when you take it step by step. The sun grows larger, the energy increases, materials are pushed closer to their limits, and systems work harder to maintain balance. Each stage builds on the last in a way that still allows for control, at least in principle. But as you continue inward, that sense of control begins to narrow. Not disappear all at once, but compress. The margin for error becomes smaller, the time available to respond becomes shorter, and the difference between stability and failure becomes more sensitive to even minor changes. This is what the final approach really means. Not a specific distance, not a clearly marked boundary, but a region where the rules you've been working with become less forgiving. Now, the physics itself doesn't change. The same principles still apply. Radiation still carries energy. Materials still absorb, reflect, and emit that energy. Gravity still shapes motion. But the scale shifts. The intensity increases to a point where those same rules produce outcomes much more quickly. And that's what makes this stage different. Because earlier, you could rely on time for systems to adjust, time for heat to be distributed and radiated away, time for small imbalances to correct themselves. Here, time becomes limited. Energy arrives faster than before, the rate of change increases, and that makes everything more demanding. Now consider what this means for a spacecraft. At greater distances, the balance between incoming and outgoing energy can be maintained with some margin. The heat shield reflects a portion of the radiation. The rest is absorbed and radiated away. The internal systems manage what remains, and as long as that balance holds, the spacecraft continues to function. But as you move closer, the incoming energy increases, not just in a linear way, but rapidly. And at some point, the equilibrium temperature of the heat shield approaches the limits of the material. The shield can still radiate energy away, but the temperature required to do so rises. And that temperature begins to approach the point where the material itself can no longer maintain its structure. Now, it's important to understand that failure here is not necessarily dramatic. It doesn't have to be an explosion or a sudden collapse. It can be more subtle, a gradual weakening, a change in material properties, a loss of structural integrity. But in this environment, even small changes can have significant consequences, because the system is operating close to its limits. Now let's think about the environment itself. Closer to the sun, the density of plasma increases. The interactions between particles and surfaces become more frequent. Radiation levels rise, magnetic activity becomes more intense. All of these factors combine, and they don't act independently, they interact. So the challenge isn't just handling one type of stress, it's handling multiple stresses at once. Heat, radiation, particle impacts, magnetic forces, each one manageable to a degree, but together they create a more complex environment. Now consider what happens when a system begins to struggle. If a heat shield absorbs slightly more energy than it can radiate away, its temperature increases. As the temperature increases, the material may become less reflective, which means it absorbs more energy, which increases the temperature further. This creates a feedback loop, one that accelerates the process. Now, earlier in the journey, there was enough margin to absorb small imbalances like this. Here, that margin is much smaller. So the same imbalance can lead to a faster progression toward failure. Now let's bring this back to the idea of distance. At large distances, moving closer by a small amount doesn't change conditions dramatically. But in this region, small changes in distance can produce significant changes in energy. So the environment becomes more sensitive, more responsive to position, and that makes precise control essential. Now, there's another aspect to consider: speed. As you fall closer to the sun, your speed increases, and that increased speed affects how you interact with the environment. Particles in the corona and solar wind collide with greater energy. Radiation exposure becomes more intense, not just because of proximity, but because of motion. So the final approach is not just about being close, it's about being close while moving very fast. And that combination increases the demands on any system trying to survive. Now let's think about what happens beyond this point, because there is a limit. Not a sharply defined line, but a region where the conditions become too intense for current materials and designs, where the equilibrium temperature exceeds what can be managed, where radiation levels become too high, where particle interactions become too disruptive. And beyond that region, maintaining a stable system becomes impractical. Now this doesn't mean that nothing can exist there. The sun itself exists there. Plasma exists there. But structures, objects designed to maintain a specific form begin to lose that ability. They transition from solid to liquid, from liquid to gas, from gas to plasma. And at that point, the idea of a spacecraft or any structured object stops being meaningful. Now there's something important about this transition. It's not about a single moment where everything fails. It's about crossing into conditions where maintaining structure is no longer possible. And that crossing depends on both distance and time. A brief pass through a region might be survivable, a longer exposure might not. So the limit is not just how close you can get, it's how long you can remain there. Now, stepping back, the final approach is where all the concepts we've discussed come together. Radiation, energy balance, material limits, motion, all of them interacting, all of them becoming more significant, and all of them contributing to the definition of how close is possible. Now, there's still one more question that naturally follows. Because even if you can't reach a solid surface, even if the sun doesn't offer a place to land, it's still worth asking. What would happen if something tried to go all the way? It helps to begin by setting aside the idea of a surface as something solid. Because when most people ask whether anything could reach the surface of the sun, they are picturing something familiar, a boundary you can arrive at, a place you could point to and say, "That's it, we've made it." Something like the ground beneath your feet, or even the surface of a planet. But the sun doesn't offer that kind of destination. What it offers instead is a gradual increase in density, temperature, and pressure, layered in such a way that the concept of a surface becomes less and less useful the closer you get. Now, from a distance, the sun appears to have a clear edge, a bright, defined disk against the sky. That visible layer, the photosphere, is often treated as the surface, simply because it's the point where light escapes freely and becomes visible to us. But physically, it isn't a surface in the way we usually mean. It's more like a transition, a region where the sun becomes opaque enough that light can no longer pass through easily from below. Above it, the gas is more transparent. Below it, the gas is denser, trapping light and scattering it repeatedly. So when you approach the Sun, you don't encounter a solid boundary, you encounter increasing resistance. Now, let's imagine continuing the journey inward, past the corona, past the outer atmosphere, moving toward this visible layer. At first, as we've discussed, the environment is dominated by radiation and sparse plasma. The density is low enough that objects can pass through without being immediately overwhelmed by direct particle interactions. Heat is still primarily a matter of radiation balance, but as you move closer, the density begins to increase, not suddenly, but steadily. More particles per unit volume, more interactions, more frequent collisions, and this changes how energy is transferred. Now, instead of radiation being the dominant mechanism, conduction and direct particle interactions begin to play a larger role. Energy is no longer just arriving from one direction, it's surrounding you more completely. And this is where the environment starts to behave less like empty space and more like a fluid. Not a liquid, not something you could swim through, but a gas dense enough to exert pressure. Now consider what happens to matter in this region. Earlier we talked about how materials respond to increasing energy, heating, weakening, melting, vaporizing, and eventually becoming plasma. As you move deeper into the Sun's outer layers, those processes accelerate. The temperatures rise to the point where most materials cannot remain solid. Metals that might withstand extreme conditions elsewhere begin to lose their structure, first softening, then melting, then vaporizing. And beyond that, the atoms themselves begin to lose electrons. The material transitions into plasma. At that point, the idea of a solid object no longer applies, because the structure that defined it has been lost. Now there's another factor, pressure. As you move inward, the weight of the layers above increases. The gas becomes denser, the pressure rises, and that pressure affects how matter behaves. On Earth, pressure can compress materials, but within a limited range. Inside the Sun, pressures become far greater, not just compressing materials, but contributing to the conditions that keep the Sun itself stable. Now, imagine an object trying to move through this environment. At first, in the outer regions, it can survive by managing radiation, reflecting energy, radiating heat away, maintaining balance. But as density increases, that strategy becomes less effective, because energy is no longer arriving only as radiation. It's being transferred through direct contact with surrounding particles. Heat is no longer something you can simply reflect away. It's something that surrounds you, and that changes the problem entirely. Now, instead of managing incoming radiation, the object must withstand being immersed in an increasingly dense hot plasma, and that is far more difficult, because there's no direction to shield against, no single source to block. The environment is everywhere. Now let's consider whether anything could survive this. With current materials and technology, the answer becomes clear. No structured object can reach deep into the Sun and remain intact, not because it would instantly explode or vanish, but because the conditions gradually remove its ability to maintain structure. It would heat, degrade, lose cohesion, and eventually become part of the surrounding plasma. Now, there's an important nuance here. Reaching the surface doesn't necessarily mean surviving there. It could mean arriving even briefly before being destroyed. So the question becomes more specific. Could anything physically reach the photosphere before it is destroyed? The answer is more complicated, because the environment near the photosphere is already extreme. Temperatures of thousands of degrees, dense plasma, intense radiation. An object approaching this region would experience rapid heating. Its outer layers would begin to vaporize before it reached the visible boundary. As material is lost, the structure weakens, and eventually the object would no longer exist in its original form. So while parts of it might reach deeper, the object as a whole would not survive the journey. Now consider this from another angle. What if you designed something specifically to reach as close as possible, using the most heat-resistant materials available, optimizing for reflection, radiation, and structural integrity? Even then, you would encounter the same fundamental limits. Because the problem isn't just temperature, it's the combination of temperature, pressure, and density, each one increasing as you move inward, each one contributing to the breakdown of structure. Now there's another interesting point. The Sun itself is not solid, but it is stable. Its structure is maintained by a balance between gravity pulling inward and pressure pushing outward. That balance creates the layers we observe. But for an external object, there is no such balance. There is no internal force maintaining structure against those conditions. So as it moves inward, it is subject entirely to the external environment, and that environment becomes dominant. Now, let's step back and consider what this means for the idea of reaching the surface. If the surface is not solid, and if the conditions near it are already destructive, then reaching it becomes less about arrival and more about transition. An object approaching the Sun doesn't arrive intact, it transitions. From a structured object to a collection of particles, from solid to plasma, and that transition begins before it reaches the visible layer. Now this might sound like a definitive answer. Nothing can reach the surface and remain itself. But there's still a subtle point to consider. Particles can. Atoms, ions, electrons, these can move through the Sun's layers. In fact, the Sun itself is made of such particles, so in a sense matter can reach the surface. But not in the form we usually think about, not as a spacecraft, not as a solid object, only as something that has already become part of the Sun's environment. Now this brings us back to the question we've been exploring. How close could you really get? If getting close means remaining intact, then the limit lies well outside the visible surface, within the corona, perhaps slightly deeper depending on design, but not all the way in. If getting close means simply reaching a certain region, regardless of what happens to the object, then the answer extends further, but the cost is the loss of structure. Now, there's one more aspect to consider. Time. Because the closer you get, the faster these transitions occur. An object might survive for a short time at a given distance, longer at a greater distance, but as you move inward, the time it can remain intact decreases. So even if something could briefly reach deeper layers, it would not remain there, it would quickly become part of the surrounding plasma. Now, stepping back, something becomes clear. The Sun doesn't allow for a simple endpoint. There's no place where you can arrive and remain unchanged. Instead, there's a continuum, a progression of conditions, each one pushing matter toward a different state, and that progression defines the limits of what is possible. Instead of thinking about the Sun as somewhere you could go, it helps to think about it as something you enter. That small shift in perspective changes everything, because throughout this journey, there has been a quiet expectation in the background. The idea that if you keep moving closer, you will eventually arrive. That there is a final point, a destination where the journey ends in a clear and satisfying way. But the closer you get to the Sun, the less that idea holds up. There is no shoreline, no solid ground, no single moment where you can say, this is it. What you find instead is a process. Now, that word can feel a bit abstract at first, but here it's actually quite concrete. A process is something that unfolds over time, a set of conditions that change gradually, each one leading into the next, and that is exactly what the Sun presents. As you move inward, the environment shifts. First, the influence of radiation increases, then the density of particles rises, then temperature and pressure begin to dominate. Each step builds on the last, and at no point does the Sun suddenly become something entirely different. It becomes more of itself. Now, let's connect this to what we've already seen. At Earth distance, the Sun is something you experience indirectly. Light and warmth arrive after travelling across vast space. They are filtered, moderated, softened. The The sun shapes your environment, but it doesn't define it completely. Move closer, and that balance changes. The sun's influence becomes more direct, more immediate, less filtered, and eventually, as you cross into regions like the corona, you're no longer just receiving energy from the sun, you're moving through it. That's the first shift from outside to inside. Now, as you continue inward, the changes accelerate, the density increases, the temperature rises, the interactions between particles become more frequent, and matter begins to respond. Not instantly, not all at once, but progressively. Structures weaken, materials transition, solid becomes liquid, liquid becomes gas, gas becomes plasma. And at that point, the distinction between object and environment starts to blur, because the object is no longer separate, it becomes part of the system it entered. Now, this is where the idea of the sun as a boundary becomes interesting, because it's not a boundary in the usual sense. It doesn't stop you at a specific point. It doesn't present a barrier you can't cross. Instead, it defines a set of conditions that gradually remove your ability to remain separate. So the boundary is not where you stop, it's where you change. Now, think about that in terms of the question we started with. How close could you really get? If you define getting close as remaining intact, as staying what you are while approaching the sun, then there is a limit, a region beyond which that is no longer possible. But if you define getting close as continuing inward regardless of what happens to your structure, then there is no single limit. You can always move further, but you do so by becoming something else. Now there's a useful way to think about this. Imagine a block of ice placed in a warm environment. At first, it remains solid. Then it begins to melt. Then it becomes water. Then, if the temperature continues to rise, it evaporates. At each stage, the substance is still there, but its form has changed. Now scale that idea up to the conditions near the sun. Instead of ice, you have metals, composites, structures. Instead of a warm room, you have an environment of increasing radiation, temperature, and pressure. The same principle applies. The form changes as conditions change, and eventually, the original structure no longer exists. Now here's where the sun differs from most environments you're familiar with. On Earth, processes like melting or evaporation happen within a larger context that remains stable. The environment doesn't change dramatically as you move through it. But with the sun, the environment itself is part of the process. It becomes more intense as you move inward. So the transformation of matter is not happening in a fixed setting. It's happening in a gradient, a continuously changing set of conditions. Now, this has an important implication. It means that there is no single answer to where the sun begins, because the transition from space to sun is gradual. The corona extends outward. The solar wind carries the sun's influence across the entire solar system. Even at Earth's distance, you are already within that extended system. So in a sense, you're already interacting with the sun, already part of its reach. But the intensity of that interaction increases as you move closer, and at some point, it becomes dominant. Now consider how this affects the idea of reaching the sun. If you imagine it as a place, you might expect a clear endpoint, a final step. But if you understand it as a process, the journey doesn't end in the same way. It transitions from observing to entering, from entering to interacting, from interacting to becoming part of the system. And that progression doesn't have a sharp boundary. Now, let's bring this back to something more concrete. Spacecraft like the Parker Solar Probe operate within this process. They don't reach a surface. They move through regions of increasing intensity. They manage energy. They maintain structure for as long as possible. And eventually, if they were to go far enough, they would also reach a point where that structure could no longer be maintained. Not because they hit something, but because the conditions no longer allow them to remain what they are. Now, there's something quietly consistent about this. The sun doesn't need to actively destroy anything. It doesn't act with intent. It simply exists, emitting energy, maintaining its structure, and anything that enters its environment responds according to the same physical laws. So the boundary is not enforced. It emerges from the interaction between matter and energy. Now, stepping back, this changes how you think about proximity. Getting close is no longer about reaching a specific distance. It's about how far you can go while maintaining a certain state, and that state depends on what you're made of, how you manage energy, how you respond to the environment. Now, for humans, that limit is relatively far out, because the body cannot tolerate the conditions that develop closer in. For spacecraft, the limit is closer, because they are designed to handle higher levels of energy, but even they have limits, and beyond those limits the same process applies. Transformation. Now, there's one more subtle point here, because while the sun represents an extreme case, the idea of a process rather than a place applies more broadly. Many things in the universe don't have clear boundaries. They transition gradually. And understanding those transitions is often more important than identifying a single point. Now, as we reach the end of this journey, the question we started with has shifted. It began as a question about distance. How close could you get? But it has become a question about interaction, about how matter responds to increasing energy, about where the limits of structure lie, and about how those limits define what is possible. Let's ease away from the sun for a moment. Not quickly, not all at once, just gradually, the way this entire journey has unfolded. After spending so much time moving inward, thinking about intensity, limits, and what happens when conditions become too much for anything to remain unchanged, it helps to shift direction, to drift back. Because even though we've explored how close you could get, the more interesting realization is that you are never completely separate from the sun to begin with. Right now, wherever you are still connected to it. The light that reached you today began its journey there. The warmth you felt, even briefly, was part of the same process we've been following, just softened by distance, filtered by atmosphere, and made comfortable by the conditions here on Earth. And that's something easy to forget. Because from this distance, the sun feels manageable, predictable, a part of your routine rather than something extreme. You wake up, it's there. You go about your day, it moves across the sky. You don't have to think about how intense it really is. Now, after moving closer in our exploration, that familiarity starts to look a little different. Not threatening, not overwhelming, but more complete. You understand that what feels gentle here is only gentle because of where you are, because of the distance, because of the layers of protection between you and the source. And that distance, that space between you and the sun, is doing a lot more work than it seems. It's spreading energy out, reducing intensity, allowing the same radiation that would be overwhelming up close to become something that supports life here. Now, as we drift back outward, imagine the sun slowly becoming smaller again. Not changing in itself, but changing in how it appears. The brightness easing, the intensity fading into something more familiar, the environment returning to something your body recognizes. And with that shift, the idea of getting close begins to soften. Because after everything we've seen, it's clear that closeness isn't just about distance, it's about interaction. About how much of the sun's energy reaches you, about how that energy is managed, absorbed, or transformed. And that means you don't have to travel millions of kilometers to experience the sun. You already do, every day. Now, think back to the beginning of this journey, the simple idea of sunlight on your skin, the quiet warmth that feels so ordinary that it's easy to ignore. That was the starting point, and it turns out it's also the ending point, because everything we've explored, radiation, energy, motion, material limits, all of it leads back to that same interaction, just at different intensities, different scales. Now there's something calming about that. The idea that the sun doesn't need to be approached directly to be understood in part. that even from here you're already connected to it, already experiencing a small, manageable version of something much more powerful, and that connection is steady, reliable. The same processes that make the sun extreme up close are what make life possible here. Now, as you settle back into your surroundings, wherever you're listening from, it's worth noticing how different everything feels compared to what we've just imagined. The air around you, the stable temperature, the absence of overwhelming brightness. All of these are part of the balance that exists at this distance, a balance that allows you to exist comfortably without needing to manage energy in the way a spacecraft does near the sun. And that balance is not accidental. It's a result of where you are, of how far you are from the source. Now, if you think about it, the question we started with, how close could you really get to the sun, doesn't have a single simple answer. It depends on what you mean by you. A human body has one limit, a spacecraft has another. Matter itself follows its own rules, and beyond all of those the sun continues, unchanged by the approach of anything that moves toward it. So the answer becomes less about a number and more about understanding. Understanding how energy spreads, how materials respond, how motion shapes the journey, and how all of those factors combine to define what is possible. Now, as we come to the end of this exploration, there's no need to rush away from the idea. You can let it settle, let the details fade a little. What remains is the sense of scale, the understanding that something so familiar can also be so extreme, and that distance plays a quiet but essential role in shaping your experience of it. Now, wherever you are, you might not be thinking about the sun in quite the same way as before, not just as something in the sky, but as something that extends far beyond what you see, something that influences everything around you even when it feels distant, and at the same time something that doesn't need to be approached to be appreciated, because even here, at this distance, you are already close enough to feel its warmth, close enough to see its light, close enough to be part of the system it shapes, and that's a comfortable place to be. So as you settle in, maybe letting your thoughts slow down a little. There's nothing more you need to figure out, no final number to hold on to, just the quiet understanding that closeness, in this case, is not about reaching the sun. It's about recognizing how it already reaches you.